Have you ever stopped to wonder how fragile our grip on reality really is? One day we believed Earth sat immovable at the universe's center. The next, we found it hurtling through space, orbiting a star among billions. And that was just the beginning. From whispers in the cosmic microwave background to fleeting radio bursts, each surprise has forced us to rewrite the rulebook of existence. Step into the shoes of the bold thinkers and careful observers who stared down orthodox wisdom and sometimes paid dearly for it. Journey from the tangled debates over the Big Bang's origin to the eerie dimming of a distant star that still has scientists scratching their heads. These stories are reminders that the universe is far stranger than we dare imagine, and that our most certain truths may one day be overturned. When the Earth stopped being the center, Heliocentrism and its heretical origins. For thousands of years, people believed that Earth stood still at the center of the universe. This was the foundation of how most civilizations understood the world and the heavens. From ancient Greece to medieval Europe, the geocentric model with Earth at the center wasn't just science, it was philosophy, it was religion, it was certainty. And then everything began to shift. A quiet man from Poland, Nicholas Copernicus, began to work on an idea that would change the course of history. Copernicus was a mathematician, astronomer, and a church official. He was well educated and deeply religious, but over years of observation, reading, and calculation, he began to doubt what nearly everyone else believed, that the Earth was fixed at the center of everything, with the sun, moon, stars, and planets all revolving around it. Instead, Copernicus proposed something radical. The sun, not the Earth, was at the center of the universe. In his model, the Earth rotated on its axis and orbited the sun, just like the other planets. This idea, simple on the surface, was revolutionary. It was more than just a change in how the stars moved. It called into question everything people thought about humanity's place in the universe. Copernicus didn't publish his ideas right away. He understood how dangerous they were. The Church taught that Earth, and by extension humankind, was the central creation of God. The Bible had verses that seemed to support this idea. To suggest otherwise wasn't just wrong, it was considered heresy. So Copernicus hesitated, revising his work again and again for over 30 years. Only near the end of his life did he allow his book, De Revolutionibus Orbium Coelestium, or On the Revolutions of the Celestial Spheres, to be printed. He reportedly received a copy on his deathbed in 1543. The reaction was slow at first. Many scholars didn't know what to make of it. Some saw it as a useful tool for calculations, but they didn't believe it described the real universe. The Catholic Church didn't move against the book immediately either, but things began to change as other scientists started taking the heliocentric idea more seriously. One of those scientists was Galileo Galilei. Using one of the earliest telescopes, Galileo looked at the moon, the stars, and the planets. He saw things no one had seen before. He observed moons orbiting Jupiter, proving that not everything revolved around the Earth. He saw that Venus had phases like the moon, which only made sense if it orbited the sun. These observations gave real support to Copernicus's model. Galileo was bold. He didn't just quietly suggest heliocentrism, he taught it. He wrote books in Italian, not Latin, so the common people could read them. He argued that the heliocentric model was not just a theory, it was truth. This brought him into direct conflict with the Church. In 1616, the Catholic Church declared that heliocentrism was formally heretical. Church authorities believed it went against the Bible and threatened the moral order. Galileo was warned to stop promoting it. For a while, he stayed quiet, but in 1632, he published a book called Dialogue Concerning the Two Chief World Systems. Though written as a dialogue between fictional characters, it clearly favored the heliocentric view, and even appeared to mock those who still supported geocentrism. This time, the Church responded with force. Galileo was called to Rome and put on trial. Under pressure, he was forced to publicly deny that the Earth moved around the sun. Legend says that as he left the court, he whispered, "And yet it moves." He spent the rest of his life under house arrest. What Copernicus started, and Galileo continued, was a deep, unsettling shift in how people saw themselves. If Earth wasn't the center of the universe, then perhaps humanity wasn't the center of creation. If the heavens followed natural laws, not divine perfection, then maybe the world wasn't as fixed and certain as people believed. This idea was terrifying to many. The old model, with Earth at the center, placed humans in a special position. The new model suggested that we were just one planet among many, circling an ordinary star in an ordinary part of the sky. That thought, more than the science itself, was what many people feared. But not everyone resisted. Some thinkers welcomed this new view. Over time, astronomers like Johannes Kepler and Isaac Newton would take the heliocentric model even further. They would develop laws of planetary motion and gravity that described the workings of the heavens with stunning accuracy. The universe was no longer a mystery wrapped in theology. It was something that could be measured, tested, and understood. Still, the path to that understanding was long and often dangerous. The Church would not officially lift its ban on books supporting heliocentrism until centuries later. The struggle over these ideas wasn't just about planets and orbits. It was about power, belief, and the right to question accepted truths. When Earth stopped being the center of the universe, everything changed. Not just in science, but in how people thought about themselves and their place in the cosmos. The shift from geocentrism to heliocentrism was one of the most important turning points in human history. It was the moment we began to look outward, not with fear, but with curiosity. The stars no longer moved around us. Instead, we were moving among them. Galileo's telescopic heresy, seeing the heavens as they are. In the early 1600s, a new instrument was making its way across Europe. The telescope, first developed in the Netherlands as a tool for spotting distant ships, soon caught the attention of scientists, including Galileo. Galileo didn't invent the telescope, but he was the first to use it in a serious and systematic way to study the heavens. He built his own versions, improving them over time until they could magnify up to 20 times. When he turned his telescope toward the sky in 1609, he saw things no one had seen before. The first target of his interest was the moon. At that time, people believed the moon, like all heavenly bodies, was perfectly smooth and flawless. The heavens were thought to be made of a divine substance, unchanging, pure, and perfect. But Galileo saw something very different. Through his telescope, he noticed that the moon had mountains, craters, and valleys. It looked a lot like Earth. This simple observation challenged the long-held idea that the heavens were fundamentally different from our world. Next, Galileo turned his attention to Jupiter. What he saw there was even more surprising. Near the planet, he spotted tiny points of light that change position from night to night. At first, he thought they were stars, but after carefully watching their movements, he realized they were orbiting Jupiter. They weren't moving across the sky with the background stars, they were circling the planet. He had discovered the 4 largest moons of Jupiter, now known as the Galilean moons, Io, Europa, Ganymede, and Callisto. This proved that not everything revolved around the Earth. If moons could orbit Jupiter, then the idea that all celestial bodies must circle Earth was simply false. This small set of moons, seen through a handmade telescope, gave hard evidence against the geocentric model. But Galileo didn't stop there. He turned his telescope toward Venus. According to the Earth-centered model, Venus should always appear as a small crescent or just a sliver of light, because it was supposed to orbit Earth inside the sphere of the Sun. But Galileo saw that over time, Venus changed shape. It went through phases. Sometimes it was a crescent, sometimes nearly full. This only made sense if Venus was orbiting the Sun. The heliocentric model predicted this perfectly. For the first time, the idea that the Sun, not Earth, was at the center of the planetary system was no longer just a suggestion. It had real backing, and that made it dangerous. Galileo published his findings in Sidereus Nuncius, or the Starry Messenger, in 1610. It created a storm. Some praised his discoveries. Others mocked them. Many refused to believe them at all. Scholars who had built their lives around the old models felt threatened. Some even refused to look through his telescope. They claimed it was a trick, or that the telescope itself created illusions. The heavens, they insisted, could not be full of imperfections. The power of Galileo's telescope was in how it forced people to confront the reality of the universe. This wasn't ancient wisdom passed down by philosophers. It wasn't religious doctrine. It was light, focused through glass, revealing things exactly as they were. It cut through centuries of tradition. This is what made it heretical in the eyes of many. The telescope didn't just support the heliocentric model, It weakened the authority of those who claimed to know the truth by faith or tradition. It suggested that the heavens could be studied like any other part of nature. Galileo knew how controversial his discoveries were, but he believed in what he saw. He wrote with confidence, even excitement. He invited others to build their own telescopes, to see with their own eyes. He didn't just want to win a debate. He wanted to change how people thought. He believed that observation and reason could reveal the workings of the universe, and for that, he paid a price. The Catholic Church, which had tolerated some of his early work, grew more alarmed as he became more vocal. The Church had long supported the idea that science and faith could go hand in hand, but only as long as science didn't challenge the core teachings of Scripture. The telescope did more than challenge them. It threatened to rewrite them. In 1616, the Church issued a warning, declaring that the heliocentric model was contrary to Holy Scripture, and told Galileo not to defend it as a fact. He agreed, at least publicly. But privately, he continued his research and writings. Years later, in 1632, when he published his most famous work, the Church saw this as a clear challenge and sentenced him to house arrest for the rest of his life. He was ordered to stay silent on the matter, even as his discoveries continued to spread across Europe. But by then, the damage to the old model was done. The telescope had opened a crack in the solid wall of geocentric thought, and there was no closing it. Others, inspired by Galileo's work, would continue where he left off. The new way of looking at the universe, through observation, through technology, through careful study, was here to stay. His instruments were simple by today's standards, just lenses held in tubes. But what they revealed was more powerful than any book, any sermon, or any long-held belief. They revealed a universe in motion, a world not fixed in place, but part of a grand, dynamic system. The Great Debate of 1920. Are galaxies just nebulae in the Milky Way? In the early 20th century, the universe was still a small place, at least in the minds of most astronomers. The Milky Way was thought to be the entire cosmos. It was a grand island of stars, gas and dust, stretching across the night sky, and almost everyone believed it held everything there was. The strange, cloudy objects known as nebulae were seen as part of it, perhaps newly forming stars, or loose gas clouds floating at the edges of the galaxy. But that belief was about to be challenged in a debate that would become one of the most important turning points in astronomy. In 1920, two astronomers, Harlow Shapley and Heber Curtis, met in Washington, D.C. for what would come to be known as the Great Debate. The event, held at the Smithsonian Institution, wasn't public in the modern sense. There were no cameras, no media frenzy, but the ideas they argued over would shape the future of how we understand the universe. Shapley and Curtis didn't see eye to eye on what the universe really looked like. Shapley, working with observations of variable stars and star clusters, believed the Milky Way was incredibly large, much larger than most thought at the time, and that all the nebulae, even the spiraling ones like the Andromeda Nebula, were inside it. To him, the universe was big, but the Milky Way held everything in it. There were no separate island universes, as some had suggested. Curtis, on the other hand, thought the Milky Way was smaller, and that those spiral-shaped nebulae were actually far beyond it. He believed they were galaxies, entire systems of stars like our own Milky Way, lying at immense distances across space. If he was right, it would mean the universe was not only much larger than anyone imagined, but also filled with other galaxies, each with billions of stars. The question at the heart of the debate was simple, but the answer would either keep the universe small or make it unimaginably large. Both men brought evidence to the table. Shapley had studied a type of star called a Cepheid variable, which changes brightness in a predictable way. By measuring the period of a Cepheid's brightness, astronomers could figure out how far away it was. Shapley used this method to measure the distances to globular clusters, tight groups of stars that orbit the center of the Milky Way. His results showed that the Milky Way was far bigger than previously thought, stretching over 100,000 light-years across, and that our Sun was not at its center. Curtis agreed with some of Shapley's numbers, but he thought they had been pushed too far. He pointed to the way spiral nebulae looked. Many had dust lanes and central bulges, just like the Milky Way. Some showed signs of rotation. He even pointed to the high speeds at which some of them moved across the sky. That motion, he argued, didn't make sense if they were close by. They had to be much farther away, outside the Milky Way altogether. The debate ended without a clear winner. There was no final answer, no vote, no agreement. The audience listened, took notes, and went home. But the ideas raised during that debate stayed in the air, waiting for the next discovery to tip the scale. That discovery came just a few years later, in 1923. A young astronomer named Edwin Hubble was working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world at the time. He pointed it at the Andromeda Nebula, one of the largest and brightest spiral-shaped objects in the sky. Through the powerful lens, he found a Cepheid variable inside Andromeda. It was the kind of star Shapley had used to measure distances. When Hubble did the math, the answer shocked him. The Andromeda Nebula wasn't in the Milky Way at all. It was over 2 million light-years away. It wasn't a cloud of gas or a nearby cluster of stars. It was an entire galaxy. Almost overnight, Curtis's view became the accepted one. The universe wasn't just the Milky Way. It was full of galaxies. Some were nearby, some were incredibly distant, and they were all flying apart from each other, as later discoveries would show. The great debate, though it ended without a winner, had cleared the way for this new vision of the cosmos. It marked a turning point between the universe we thought we knew and the vast, expanding universe we now explore. It showed how science often works, not in sudden dramatic shifts, but through careful argument, disagreement, and slow, steady gathering of evidence. The role of technology in this moment was just as important as the ideas. Without the telescope at Mount Wilson, Hubble wouldn't have seen the stars in Andromeda. Just like Galileo's telescope had brought the moons of Jupiter into focus, the Hooker telescope had brought the scale of the universe into view. Before, people had looked at the night sky and saw mystery. After it, they saw structure, distance, and scale beyond imagination. The stars weren't scattered across a single galaxy. They were grouped into billions of galaxies, each with its own stars, planets, and perhaps even life. The Great Debate pushed astronomers to ask bigger questions and to look farther. It opened the door to a universe that was far more complex and far more beautiful than anyone had dared to believe. In the years that followed, Hubble continued his work. He found more galaxies, all racing away from each other, leading to the idea of an expanding universe. That would later become the foundation for the Big Bang theory. But it all started with a question debated in a quiet hall in Washington. A question that seemed simple, but turned out to hold the key to the shape of everything. A universe that's growing, the radical implications of Hubble's redshift. By the late 1920s, astronomers had accepted that the spiral nebulae were galaxies, and that the universe was made up of many such systems. But Hubble wasn't finished. He had started looking at the light from these galaxies in more detail. He noticed something strange. When the light from distant galaxies was passed through a prism, it spread out into a spectrum, just like sunlight through a glass of water. In that spectrum, there were dark lines. These lines, caused by the elements in the stars, were like fingerprints, showing what the galaxies were made of. But the problem was that these lines weren't where they were supposed to be. They were shifted, pushed toward the red end of the spectrum. Hubble had seen this kind of shift before. It was called redshift. The idea wasn't new. In fact, the Doppler effect, where sound or light waves change as the source moves, was already known. When a train moves toward you, its whistle sounds higher, and when it moves away, it drops lower. Light works the same way. If a light source moves toward you, its light shifts slightly toward the blue. If it moves away, it shifts toward the red. So if the galaxy's light was redshifted, that meant they were moving away. At first, it was just a curiosity, but then Hubble began measuring the redshift of more galaxies. And the farther away they were, the more redshifted their light became. In other words, The more distant the galaxy, the faster it was moving away from Earth. This wasn't just one galaxy drifting off. This was everything, all galaxies, rushing away from each other. The universe wasn't standing still. It was expanding. The idea was hard to grasp. For centuries, people thought the universe was fixed. The stars stayed in place. The galaxies spun in silence. Even the early heliocentric model had kept space still while the planets orbited the sun. Newton's physics had supported that view, picturing a great cosmic clock ticking along, but not changing in size. Now, Hubble's findings were saying something entirely different. The universe itself was growing. It wasn't like an explosion where matter was pushed outward into empty space. It was space itself that was stretching. Every point in the universe was moving away from every other point, like spots on the surface of an inflating balloon. From any location, it would look like all other places were rushing away. There was no center, no edge, just expansion. Hubble's discovery spread quickly through the scientific world. Physicists, cosmologists, and even philosophers began wrestling with what it meant. If the universe was expanding, then it must have been smaller in the past. If you rewind that expansion, you reach a moment when everything was compressed together, perhaps even into a single point. This was the start of an idea that would later be known as the Big Bang. But not everyone liked it. The thought of a dynamic, changing universe was uncomfortable to many. Some scientists held on to the idea of a steady-state universe, one that had always existed and always would. They believed matter was somehow created as space expanded, keeping the overall density of the universe the same. It was neat, and it felt more in line with tradition. But the data from Hubble's telescope didn't support that view. The telescope had captured it, and no one could deny it. As more telescopes scanned the skies, and as better instruments were developed, the redshift measurements grew more precise. The pattern remained. Galaxies were moving away. The universe was expanding. Hubble wasn't working alone. His colleague, Milton Humason, helped him gather the data, often working long hours in cold conditions, taking photographic plates and measuring spectral lines. The work was slow and meticulous. Each measurement had to be done by hand, with great care. But the result was clear and repeated over and over again. The expansion was real. Years earlier, the idea of an expanding universe had appeared in theoretical work, especially in the equations of Albert Einstein. But Einstein himself didn't believe it at first. When he solved the equations of general relativity, they seemed to suggest that the universe should be either expanding or contracting. To avoid this, he added a term to his equations, a cosmological constant, to hold the universe in place. After Hubble's discovery, Einstein reportedly called the cosmological constant his greatest blunder. The universe didn't need to be held still. It was on the move, expanding on its own. From that point on, cosmology, the study of the universe's origin and structure, became a science based not just on ideas, but on observation. The universe had a story, and that story could now be traced through redshifts, distances, and time. The farther out you looked, the farther back in time you saw. Every galaxy became a kind of time machine, offering a glimpse into the past, into a younger and smaller universe. Hubble's redshift findings also meant that the universe had a beginning, something that earlier models didn't really consider. If the universe had a starting point, it opened the door to new questions. Questions about what came before, about what caused it, and about how it might end. The expanding universe didn't answer all the questions. In fact, it raised many more. But it marked a turning point, one as important as Copernicus's shift away from Earth-centered thinking or Galileo's view of the heavens through a telescope. It was another moment when the cosmos became larger, older, and stranger than anyone had imagined. And once again, Earth, along with everything on it, seemed smaller, not in meaning, but in scale. The story of the cosmos had just grown much bigger. Echoes of creation, why the discovery of the cosmic microwave background was so contested. In the early 1960s, two radio engineers, Arno Penzias and Robert Wilson were working at the Bell Telephone Laboratories on a large horn-shaped antenna. The antenna had originally been designed for satellite communication, but Penzias and Wilson were using it to detect faint radio waves from the sky. No matter where they pointed the antenna, they kept picking up a persistent background noise, steady, uniform, and coming from every direction. They checked their equipment over and over. They looked for interference from nearby cities, from the sun, even from pigeon droppings in the antenna. Nothing they did made the noise go away. It was just there, a soft, steady hum at microwave frequencies, with no clear source. At first, it seemed like an annoyance, just another obstacle in their work. But they kept listening. What Penzias and Wilson didn't know at the time was that this signal had been predicted years earlier by scientists working on a very different idea. Back in the 1940s, physicists including George Gamow, Ralph Alpha, and Robert Herman had suggested that if the universe had started in a hot, dense state, a kind of explosion or bang, then the leftover heat from that moment should still be around today. Over time, this heat would have cooled and stretched out as the universe expanded, shifting into the microwave part of the electromagnetic spectrum. They called it the relic radiation of the Big Bang. But in the years that followed, few took the idea seriously. The steady-state model of the universe was still strong. According to that model, the universe had no beginning and no end. It simply existed, expanding but always staying the same in terms of density and structure. Then came the noise from Holmdel. As Penzias and Wilson continued to investigate, they heard from a group of physicists at nearby Princeton University, including Robert Dicker and Jim Peebles. Dicker and his team had been working on a way to detect the leftover heat from the Big Bang, the same kind of signal Penzias and Wilson were hearing. But the engineers had already found it, by accident. When the two teams talked and shared data, the pieces fell into place. What Penzias and Wilson had discovered was the cosmic microwave background, or CMB, the faint afterglow of the universe's birth. It was a nearly perfect match for what the Big Bang theory predicted. Uniform, isotropic, and present in every part of the sky, the signal carried a temperature of about 3 degrees above absolute zero. It was exactly the kind of radiation that would remain from a hot early universe that had cooled over billions of years. The discovery was soon published in 2 back-to-back papers in the journal Astrophysical Journal Letters, one by Penzias and Wilson describing their detection, and the other by Dicker's group explaining what it meant. Together, these papers made a simple but stunning point. The Big Bang had left behind a trace, and it was still glowing. The reaction was not immediate. Some scientists still hoped the signal could be explained another way. Maybe it came from distant stars, or clouds of gas, or something else entirely. But as measurements improved over the next several years, those alternatives faded. The cosmic microwave background had a spectrum that matched exactly what a hot blackbody should give off, a form of radiation tied directly to temperature. It wasn't coming from stars or gas, it came from the universe itself. The discovery of the CMB didn't just support the Big Bang model, it crushed the steady-state theory. Slowly but surely, the scientific community began to shift. By the late 1970s, the Big Bang was no longer just a possibility. It was becoming the accepted explanation for the origin of the universe. But the story of the CMB didn't end with its discovery. It became a powerful tool for learning more about the universe's history. In the 1990s, NASA launched the Cosmic Background Explorer satellite, or COBE, to map the CMB with more detail. What COBE saw was not just a smooth glow, it found tiny fluctuations in the temperature of the CMB, patterns that showed the seeds of structure in the early universe. These were the places where matter had clumped just slightly more than average, places where galaxies would later form. Later missions like WMAP and Planck would map the CMB in even more detail, giving scientists a picture of the early universe just 380,000 years after the Big Bang. In that baby picture of the cosmos, they could read the shape, age, and composition of the universe itself. It told them how much matter there was, how much dark matter, and how much dark energy. It told them how fast the universe was expanding and what kind of geometry it had. None of this would have been possible without the chance discovery of a noise in a radio antenna. A noise that turned out to be the oldest light in the universe. The CMB became a relic, a time capsule from a moment when the universe changed forever. Fred Hoyle versus the Big Bang. Fred Hoyle did not believe in a beginning. To him, the idea that the entire universe sprang from a single explosive moment seemed not only strange, it seemed deeply unscientific. Hoyle was a man of reason, structure, and skepticism. The universe should follow patterns, and those patterns should not start or stop without cause. In his view, the cosmos was eternal, constant, and unchanging in its broadest features. It had no beginning and would have no end. New stars would form as old ones died, but the universe itself would go on forever, always looking more or less the same on the largest scales. This was the steady-state model, and for a time, it was a serious rival to the Big Bang. Hoyle wasn't alone in promoting the idea. In the late 1940s, he worked closely with two other British scientists, Thomas Gold and Hermann Bondi. Together, they proposed a version of the universe that expanded, yes, but only in a way that kept things balanced. As galaxies moved farther apart due to cosmic expansion, new matter would be created in the gaps. That new matter would eventually form new galaxies, keeping the overall density of the universe the same. The math worked. The universe could grow, yet still maintain its appearance forever. To many scientists, especially those wary of metaphysical ideas creeping into science, this was a comforting picture. The steady-state model didn't require a moment of creation. It didn't require a cause for the universe itself. It simply was. Always had been. Always would be. But not everyone agreed. A separate group of scientists, including Gamow and his colleagues Alpha and Hermann, were working on something different. They were building on earlier ideas from Einstein and Georges Lemaitre, who had suggested the universe was expanding from a dense initial state. These scientists believed the cosmos had started in an extremely hot, compact condition and expanded from there, a model that would later be called the Big Bang. Ironically, it was Hoyle himself who gave the model its name. In 1949, Hoyle appeared on a BBC radio broadcast. While describing the rival theory, he called it the Big Bang, somewhat sarcastically, trying to highlight what he thought was a ridiculous notion that the entire universe had once been squeezed into a tiny point and exploded outward. But the name stuck, people liked it, and the Big Bang soon became a household term. Still, Hoyle fought back. For years, he continued to refine the steady-state theory. He found supporters and built arguments. He pointed out problems in the Big Bang model, such as its reliance on early conditions that couldn't be tested, or the strange assumption that everything came from nothing. Hoyle was especially bothered by what he saw as a religious tone in the Big Bang. This idea of a beginning sounded too much like Genesis, too much like the kind of answers science was meant to avoid. To Hoyle, the universe was a machine. It had rules, and it shouldn't have needed a beginning. His model included one bold addition: the continuous creation of matter. According to steady-state theory, matter had to appear in empty space at just the right rate to fill in for the loss caused by expansion. Hoyle suggested this happened spontaneously, on scales too small to detect. It was a small act, repeated constantly across the cosmos. It allowed the universe to grow while never really changing. For a time, the scientific community was divided. The Big Bang explained things well, but it lacked direct observational proof. The steady-state model seemed elegant, even if it required new physics. Both sides made predictions. Both sides had followers. The arguments went beyond equations. They touched on deep questions about what kind of universe we live in. Then, in the 1960s, came the discovery that changed everything: the CMB. Hoyle tried to respond. He and his supporters worked to modify their model. They suggested alternative sources for the radiation. They proposed secondary mechanisms to match the data, but none of it was enough. Over time, the observations became too clear, too consistent with the Big Bang, and not with steady-state ideas. The argument moved from data to history. Hoyle never gave up. Even as the majority of cosmologists moved toward the Big Bang model, he kept questioning it. He continued publishing papers, suggesting new forms of matter and exotic particles. He challenged the assumptions behind the expanding universe. In some ways, it wasn't just science for him, it was principle. He had spent his life building a view of the cosmos based on balance and permanence. He believed that the rules of the universe should be universal, that creation and destruction should be part of a continuous natural cycle. The Big Bang, in his view, was not just wrong, it was too simple, too abrupt. It asked people to accept the idea that everything came from a single, unexplained moment. That didn't feel like physics to him. That felt like myth. In later years, Hoyle's resistance grew more isolated. The data kept piling up. Missions like COBE, WMAP, and Planck mapped the CMB in ever greater detail. All of it fit the Big Bang model better than any alternative. Still, Hoyle remained firm. He didn't soften his stance. He believed that the scientific community had closed ranks too quickly, that they were chasing a popular model rather than following all the evidence. To some, he became a symbol of scientific courage. To others, he was simply stubborn. In his struggle, Hoyle played a vital role. He sharpened the debate. He asked hard questions. He made the Big Bang model stronger by forcing its supporters to back it up with evidence. In challenging the mainstream, he made the mainstream better. He never accepted the Big Bang. But the universe he loved, ordered, lawful, filled with stars and mystery, became more real because of the arguments he sparked. The missing mass crisis, when galaxies refused to obey Newton. In the middle of the 20th century, astronomy was settling into a kind of confidence. The Big Bang model had taken hold. Telescopes were getting stronger. New techniques let scientists measure galaxies, stars, and gas clouds more precisely than ever. The laws of physics, especially Newton's laws of motion and gravity, seemed to explain nearly everything they could see. The universe was vast, but it appeared understandable. But that sense of order would not last. Something was off. Galaxies, it turned out, were not moving the way they should. It started with measurements of spiral galaxies, the kind with pinwheel-like arms twisting out from a bright central bulge. These galaxies rotate, and astronomers began to track how fast stars were moving at different distances from the center. According to Newton's laws, objects farther out from the center should move more slowly, just like the planets in our solar system. Mercury, close to the Sun, moves quickly. Neptune, far away, moves slowly. The pull of gravity weakens with distance, so orbital speed should fall as you go farther out. That was what physicists expected galaxies to show too. But that isn't what happened. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made careful measurements of these galactic rotation curves. Rubin used a sensitive spectrograph to track the speeds of stars and gas on the outer edges of spiral galaxies. What she found instead was that the stars on the outskirts of galaxies weren't slowing down at all. They were moving just as fast as stars much closer to the center. In some cases, they were moving even faster. That was not supposed to happen. If galaxies only had the visible matter, the stars, gas, and dust that telescopes could see, then gravity shouldn't be strong enough to hold the fast-moving outer stars in place. Those stars should be flying off into space, but they weren't. Something invisible seemed to be keeping them there, adding extra gravity that wasn't accounted for in the usual models. Rubin's data was careful and consistent. She looked at dozens of galaxies. The pattern was the same, flat rotation curves, not the steep drop-offs expected under Newtonian gravity. Either the laws of gravity were breaking down at large scales, or there was more matter out there, something we couldn't see, but that had mass and pulled on stars just like regular matter did. that invisible mass needed a name. Astronomers began calling it dark matter. The term had been used before, but now it took on a more specific meaning. Dark matter wasn't just a catch-all term for unknown stuff. It was becoming a real part of astrophysical models. It had to be something that didn't emit or reflect light. It couldn't be ordinary stars, planets, or dust clouds. Those would have been visible, or at least detectable. Whatever this missing mass was, it didn't interact with light at all. It was dark in the truest sense. Rubin wasn't the first to suggest something strange was going on. Decades earlier, in the 1930s, the Swiss astronomer Fritz Zwicky had looked at galaxy clusters and found something similar. He measured the speeds of galaxies moving within the Coma cluster and realized they were moving so fast that the whole cluster should have flown apart. The visible matter wasn't nearly enough to hold them together. He estimated that there must be hundreds of times more unseen mass than seen mass. He called it dunkle Materie, German for dark matter. But at the time, his ideas were largely ignored. He was known for being eccentric, and without more evidence, few people took the claim seriously. It wasn't until Rubin's work decades later that the idea truly caught on. Her observations were clear, reproducible, and based on individual galaxies, not giant clusters. And they came at a time when astronomy had the tools to examine these claims in detail. The missing mass problem grew. It wasn't just in spiral galaxies, elliptical galaxies, galaxy clusters, even the cosmic web that linked everything together. All seemed to require far more mass than what was visible. Some astronomers tried to fix the problem by adjusting the laws of gravity. The idea was that maybe Newton's law didn't apply the same way at galactic scales. These modified gravity theories had some success, but they struggled to explain all the data at once. Dark matter, as strange as it sounded, seemed to offer a simpler solution. A form of matter that interacts through gravity, but not through light. It wasn't only stars and galaxies that hinted at this hidden mass. In the coming years, other kinds of measurements would add support to the dark matter picture. Gravitational lensing, when light from distant galaxies is bent by the mass of objects in front, revealed distortions that couldn't be explained by visible matter alone. The lensing patterns showed that much of the mass in the universe was unseen. Temperature maps of the CMB also showed patterns that depended on how much matter was in the early universe. The data matched what astronomers would expect if there were about 5 times more dark matter than regular matter. Again and again, dark matter appeared to be the best fit. But while the evidence piled up, the identity of dark matter remained elusive. Scientists proposed all sorts of candidates. Some thought it might be a new kind of particle, called a WIMP, short for weakly interacting massive particle. Others proposed axions, sterile neutrinos, or even entire populations of black holes. But none of these candidates have yet been confirmed. Even so, dark matter became part of the standard model of cosmology. Without it, galaxies wouldn't form the way we see them. Structures in the universe wouldn't have had time to grow. Stars wouldn't be where they are now. The math just doesn't work without it. Vera Rubin's data revealed a crack in the foundation of physics. Something big, heavy, and invisible is shaping the universe. And we still don't know exactly what it is. The missing mass crisis didn't end with an answer. It opened a door. Today, observatories around the world, deep underground, high on mountaintops, floating in space, are searching for dark matter. They're trying to catch a glimpse of it, to see it scatter off a particle or leave a tiny signal behind. So far, it has stayed hidden, but the stars still spin too fast. The galaxies still cling together, and the universe still pulls in ways that visible matter cannot explain. Whatever it is, dark matter is out there, quiet, invisible, and essential. The Methusela Star, older than the universe. In the early 2000s, astronomers came face to face with a seemingly impossible star. It was a single, quiet star in our own galaxy, not all that remarkable in brightness, location, or movement. But when scientists tried to figure out how old it was, the numbers didn't make sense. This star, known today as HD 140283 and nicknamed the Methusela Star, seemed to be older than the universe itself. At the time, the universe was estimated to be around 13.8 billion years old, based on measurements of the CMB and the rate of expansion. The Methusela Star, on the other hand, appeared to be 14.5 billion years old, give or take 0.8 billion years. Even with a margin of error, the lower limit still brushed dangerously close to the upper age of the entire universe. If that star truly formed before the Big Bang, it would mean everything we understood about the cosmos was wrong. The first thing astronomers had to consider was how the star's age was measured. Age dating stars involves some of the most careful work in astronomy. Scientists look at the star's color, its brightness, and most importantly, its chemical composition. The Methusela Star turned out to be extremely low in metals. In astronomy, metals means anything heavier than helium. A star with low metal content likely formed early in the universe's history, before many supernovae had time to scatter heavier elements into space. That already marked it as ancient. But age estimates go beyond chemical content. By using models of stellar evolution, how stars change over time based on their mass and makeup, astronomers can simulate how a star like Methusela would have burned its fuel. These models showed that it had been burning steadily for billions of years. Based on how far along it was in its life cycle, it must have started burning very shortly after the universe came into existence. And that's where the numbers began to clash. So how could one star be older than the universe? At first, many assumed it had to be a mistake, an error in the models, or in how the data was interpreted. But the problem kept showing up, even as measurements improved. If it wasn't a calculation error, maybe it pointed to something deeper. Some scientists wondered if the models used to measure stellar ages might be missing something. Tiny changes in a star's interior structure or in how certain elements behave under pressure might throw off the clock by hundreds of millions of years. There was also the question of distance. If Methusela was slightly closer than expected, it would appear dimmer and thus older than it really was. To be clear, not everyone thought the Methusela Star truly broke the rules. Some scientists pointed out that the margin of error could still bring its age below the universe's age. Others thought there might be rare chemical processes in ancient stars that we hadn't fully grasped. But the fact that the two values came so close, and sometimes crossed, created tension in cosmology. The mystery became part of a broader discussion about how the age of the universe is calculated. Different methods don't always agree. Using the CMB gives one answer. But measuring the expansion rate of nearby galaxies, the Hubble constant, can give slightly different answers depending on how it's done. This has created what some researchers call the Hubble tension, a growing problem in cosmology where different ways of measuring the same thing produce incompatible results. The Methusela Star fits into this larger puzzle. It doesn't just challenge the timeline of one model, it casts doubt on whether all the clocks in the universe are ticking at the same speed. If the star is truly older than the universe, something fundamental has to give. Either the star's age is wrong, the universe's age is wrong, or our understanding of time itself may be incomplete at the largest scales. There are other stars like Methusela too. A small population of ultra-metal-poor stars has been found in the Milky Way's halo, the spherical region of older stars that surrounds the galaxy. These stars are likely among the first ever formed. Some may have been born just a few 100 million years after the Big Bang. Studying them is like looking into a time machine. Each one is a fossil from an age when the universe was young, hot, and almost entirely made of hydrogen and helium. These stars are rare and faint. Finding them takes powerful telescopes and careful analysis. But as astronomers discover more of them, they may help refine the models of stellar aging. White holes, theoretical rebels in the physics of time. White holes come from the same equations that gave us black holes, but they behave in the opposite way. Where a black hole pulls in everything, a white hole pushes everything away. It's a mirror image. The story starts with Albert Einstein's theory of general relativity. These are the equations that describe how gravity works as the bending of space and time. In 1915, they changed the way scientists understood the universe. A few years later, in 1916, a German physicist named Karl Schwarzschild found a solution to these equations. That solution would become what we now call a black hole. But when physicists looked more closely at Schwarzschild's solution, they found there was a second side to the equation, a mirror side. It was not a black hole, it was the opposite. If a black hole is a one-way trap where matter and energy fall in and never come out, a white hole is a one-way source where matter and energy shoot out, but nothing can get in. At first, this was just a mathematical curiosity. No one had seen a white hole. There was no reason to believe they existed, but in theory they were possible. General relativity did not forbid them, and that opened up a strange kind of debate in physics, one where the evidence was not in the stars, but in the logic of the laws themselves. The biggest issue with white holes is time. If black holes are regions where space collapses inward, then white holes are regions where space explodes outward. But more importantly, white holes run backward through time. That doesn't mean they move in reverse, like rewinding a video. It means that if you flipped time itself, a black hole would become a white hole. This idea of time reversal is not new in physics. Many laws of nature don't care which way time flows. If you run the equations backward, they still work. But our experience of the universe is not like that. Time has a direction. We remember the past, not the future. We grow older, not younger. And black holes form when stars collapse. A white hole would have to appear suddenly, without a cause, spitting out matter from nowhere. This is where the controversy begins. Many physicists argue that white holes cannot exist in the real universe. Not because general relativity says so, but because everything else we know about nature resists it. White holes would break the usual flow of cause and effect. They would require highly specific conditions to appear, conditions that are so perfect and so unlikely that they seem impossible. But others say we shouldn't be too quick to rule them out. The universe has a long history of surprising us. Black holes, once thought impossible, are now part of the standard picture of how galaxies form. They have been detected by the light they bend, the matter they swallow, and even the ripples in space they create when they collide. If white holes are the other side of the same equation, maybe they have a role too. One place where white holes have shown up in theory is in the idea of wormholes. These are tunnels through space-time, shortcuts from one point in the universe to another. A wormhole would need two ends, a black hole to pull things in and a white hole to push them out. In theory, someone could travel through the wormhole and come out somewhere else, maybe even someone else. But these models are full of problems. They require strange matter with negative energy, which we've never seen, and they may collapse before anything can pass through. Another idea is that a white hole might be what comes out the other side of a black hole. Right now, when something falls into a black hole, we say it disappears beyond the event horizon. At the center is a singularity. But some physicists wonder if there might be more. If space and time continue past the singularity, maybe the matter comes out elsewhere in the form of a white hole. Some models of quantum gravity, an attempt to combine general relativity with quantum mechanics, suggest that the core of a black hole might not be a true singularity. Instead, it might be a bounce. Space compresses, reaches a maximum point, and then expands again. On the outside, it looks like a black hole. On the other side, it looks like a white hole. This idea has been explored in loop quantum gravity, one of the main theories trying to go beyond Einstein. In this model, black holes might not last forever. They might shrink and transform into white holes over time, slowly releasing the matter they once trapped. This could offer a way out of one of the biggest problems in physics, the black hole information paradox. If white holes exist, maybe nothing is truly lost. Still, these are only theories. No one has observed a white hole. There are no known signals in the sky that match what a white hole would produce. A few gamma-ray bursts and other high-energy events have been speculated to be white hole outbursts, but there's no proof. Until such evidence appears, white holes remain mathematical rebels, allowed by the rules, but unwanted by the rest of nature. If white holes can exist, then time may be more flexible than we think. The future could loop into the past. The beginning of one thing could be the end of another. And events might happen not because of causes, but because of symmetry. That kind of thinking goes against the grain of how we usually do science. But it might be the only way to explain the full picture. White holes ask us to consider what is natural and what is possible. Just because something is rare or strange doesn't mean it isn't real. The universe is not required to follow our expectations. It only has to follow its laws. And those laws, as written by general relativity, leave the door open to white holes. For now, that door is mostly symbolic, but it remains open. As physicists dig deeper into the structure of time and space, we may one day find signs of something bursting outward from nothing. Until then, white holes remain on the edge of imagination, a puzzle made of math, waiting for the universe to tell us whether it belongs in reality. Black holes before we believed, why Einstein thought they were impossible. The idea of what we now call black holes came from a solution of Einstein's equations. It described how space and time would behave around a point mass, an object so dense and small that its gravitational pull would become infinite at its center. At a certain distance from this mass, called the event horizon, the escape velocity would be greater than the speed of light. Once something crossed that line, it could never come back out. Carl Schwarzschild's solution was simple, but strange. It had a singularity at its center, a point where the curvature of space-time became infinite. And the boundary around it, the event horizon, acted like a one-way door. Light could enter, but it couldn't leave. Space inside would collapse inward, and time itself would point toward the center. But for decades, physicists, including Einstein, treated it as a mathematical trick, not a physical object. The idea seemed too strange, too extreme. A collapsing star forming an invisible trap? It didn't fit with how people saw the universe back then. Einstein himself wrote papers trying to show that these objects couldn't form. In 1939, he published a study arguing that, under realistic conditions, gravity wouldn't be strong enough to make matter collapse that far. He believed that nature would resist such extremes. Somehow, internal pressure or energy would always push back. At the same time, other scientists were starting to take the idea more seriously. One of them was J. Robert Oppenheimer, the physicist who would later lead the Manhattan Project. Also, in 1939, Oppenheimer and a colleague, Hartland Snyder, published a paper that said something very different. They showed that if a star were massive enough, and if it ran out of fuel, nothing could stop its collapse. The star would keep shrinking, faster and faster, until it crossed the event horizon and disappeared. From the outside, it would seem to freeze in time as it fell, but from its own point of view, it would fall all the way to the singularity. Yet even after this paper, the idea didn't gain traction. For most physicists at the time, black holes still felt too exotic. There were no telescopes that could see such things. There were no observations to suggest they existed, and without evidence, most scientists stayed cautious. The term black hole didn't even exist yet. That would come later, in the 1960s, from physicist John Archibald Wheeler. Before that, people used terms like frozen star or gravitationally collapsed object. Einstein's doubts were partly about the physical world and partly about how he saw nature. He didn't like singularities, places where the laws of physics broke down. He thought the universe should be smooth and continuous. A black hole, with its infinite density and one-way boundary, felt unnatural to him. He expected the equations to fail before reaching such a place. He trusted the theory, but not its more extreme predictions. It wasn't until the second half of the 20th century that things began to shift. New work in astrophysics brought the idea back into focus. Stars, people realized, could come in different sizes, and their deaths followed different paths. Small stars like our Sun would end as white dwarfs. Larger ones could become neutron stars. But what about the truly massive ones? Stars 10 or 20 times the mass of the Sun. For them, no known force could stop the collapse. Their cores would fall inward without end. And that's where black holes re-entered the picture. In the 1960s, as new observations of the sky revealed mysterious and compact sources of X-rays and radio waves, scientists began to wonder if these might be the long-theorized collapsed stars. Cygnus X1, a powerful X-ray source discovered in 1964, became one of the first serious black hole candidates. Its behavior suggested it was a massive, invisible object pulling matter from a nearby star. As the material spiraled in, it heated up and emitted X-rays, just the kind of activity a black hole would produce. By the early 1970s, black holes had gone from being math curiosities to serious subjects of study. Physicists like Stephen Hawking, Roger Penrose, and Kip Thorne helped to shape the new understanding of these objects. They developed theories of how black holes spin, how they might evaporate through quantum effects, and how they distort time. The same equations that once seemed too extreme now became tools to explore deep questions about reality. Yet it's important to remember how long the road was to get there. Even with equations pointing the way, even with models predicting collapse, the physics community resisted. Not just because of the lack of data, but because the idea itself was hard to accept. The universe, as it was imagined in the early 20th century, was a place of balance. Stars burned steadily. Space was smooth, time marched on. A place where space collapses and time twists on itself didn't fit that picture. Einstein thought there would always be something to stop the collapse: pressure, repulsion, or maybe a new law yet to be discovered. He believed singularities were a sign that a theory had gone too far. In that way, he saw black holes not as real objects, but as warnings from the equations. Ironically, Einstein's theory turned out to be more radical than he expected. General relativity didn't just explain the bending of starlight or the orbit of Mercury. It pointed to deep invisible structures in the universe, places where space itself could tear, fold, and trap. The very equations he tried to tame gave rise to the wildest beasts in the cosmos. Now, black holes are everywhere in astronomy. They sit at the centers of galaxies. They power quasars. They collide and send out gravitational waves. And they still puzzle physicists who try to understand what happens at their core and what secrets might lie beyond the event horizon. Neutron stars that should collapse but don't. Neutron stars are among the strangest objects in the universe. They are what's left after a giant star explodes. If the star isn't massive enough to become a black hole, it collapses into a sphere just a few kilometers wide, roughly the size of a city, but with more mass than our Sun. The matter inside is crushed so tightly that atoms no longer exist in their usual form. Electrons and protons are squeezed together to become neutrons, and the whole thing becomes one enormous ball of nuclear matter. For decades, astronomers believed there was a clear dividing line. A neutron star could only be so heavy before it would collapse into a black hole. This line, called the Tolman-Oppenheimer-Volkoff, or TOV limit, is like a pressure limit in the heart of a dying star. Go over it, and gravity wins. Go under it, and neutron pressure can hold the collapse off. This idea gave scientists a fairly stable way to understand the aftermath of stellar death. But as telescopes and measurement tools got better, some neutron stars were found to be just too massive. They seemed to exist well above the predicted limit. According to current theories, they shouldn't be able to survive without collapsing, yet somehow they did. One of the earliest hints of this came from a neutron star named PSRJ, 1614-2230. Discovered in 2010, this star was part of a binary system, meaning it had a companion star orbiting it. By measuring the timing of its radio pulses and the gravitational pull it exerted, astronomers could calculate its mass. The result was surprising, about 2 times the mass of the Sun. That might not sound like much, but for a neutron star, it was extraordinary. Most known neutron stars fall somewhere between 1.2 and 1.4 solar masses. This one broke through what was thought to be the safety zone. Not long after, another neutron star, PSR J0348 plus 0432, was found with a mass of about 2.01 solar masses. Each new finding pushed the limits of what physicists thought neutron stars could withstand. In 2019, PSR J0740 plus 6620 was measured at about 2.14 solar masses, making it one of the heaviest neutron stars ever found. These stars challenge the line between neutron stars and black holes. According to theory, gravity at these masses should crush even the neutrons themselves. The internal pressure that holds up the star should no longer be enough, yet here they are, spinning, pulsing, stable. To understand why this is such a problem, it helps to think about what holds a neutron star up. In a normal star, heat and pressure from nuclear fusion push against gravity, but in a neutron star, fusion has stopped. The only thing resisting gravity is something called neutron degeneracy pressure, a quantum effect that comes from the fact that neutrons, like electrons, don't like to be in the same place or the same energy state. This is the same principle that holds up white dwarfs, only with electrons instead of neutrons. But even degeneracy pressure has its limits. At some point, the density becomes so high that neutrons themselves can't hold the star up. The TOV limit tries to describe that boundary. But what if there's more going on inside these stars than we expect? One idea is that the matter inside the most massive neutron stars might not be made of just neutrons. Under extreme pressure, neutrons might break down into smaller particles, quarks. These are the basic building blocks of protons and neutrons. If this happens, the star could become what's known as a quark star. Such a state of matter might be able to resist collapse more strongly than pure neutron matter. Another possibility is that the equation of state, the relationship between pressure and density inside these stars, is wrong or incomplete. The physics of dense nuclear matter is still not fully understood. In laboratories on Earth, we can't recreate these kinds of pressures. So scientists rely on theory, computer models, and indirect measurements from space. If we've underestimated how strong nuclear forces can be at extreme densities, then neutron stars might be able to survive at higher masses than expected. Some neutron stars, known as magnetars, have incredibly strong magnetic fields, billions of times stronger than anything on Earth. These fields might help support the star against gravity, though the exact mechanics are still being studied. Rotation adds another layer to the mystery. A spinning neutron star can support more mass than one that isn't spinning. The centrifugal force from its rotation gives it extra resistance against collapse. This means that a fast-spinning neutron star might appear stable even if its mass is near or above the usual limit. But this trick only works temporarily. Over time, the star loses energy and slows down. If it slows too much, it could eventually collapse into a black hole. There's a chance that we're seeing these stars at a lucky moment, right before they collapse. Maybe these stars are in a kind of temporary balance, a final pause before gravity finally wins. In that case, their existence would still follow the rules, just with very short timing. But the number of massive neutron stars found so far suggests this isn't just chance. All of this points to one thing. We still don't fully understand what happens inside neutron stars. They are like laboratories for the universe's most extreme physics. Every new discovery puts more pressure on existing theories. The boundary between neutron stars and black holes is no longer sharp. It's becoming a wide, uncertain zone where new forms of matter might exist and where the rules of pressure, gravity, and quantum mechanics get rewritten. Gravitational wave astronomy has added even more pieces to the puzzle. When neutron stars collide, they send out ripples in space-time. By studying these waves, scientists can learn about the star's masses, sizes, and internal structure. The famous event GW 170817, detected in 2017, came from two neutron stars merging. It gave us data on how much mass was involved and what kind of object the merger produced. Some models suggest that the final object may have been a hypermassive neutron star, again pushing past known limits. Maybe we'll discover new states of matter. Maybe the rules of quantum gravity will help explain what happens at these edges. But for now, the massive neutron stars that spin quietly in the dark remain unanswered questions. The galactic core mystery: why isn't our supermassive black hole more active? At the center of our galaxy, buried beneath clouds of gas and dust, lies a monster. It's a supermassive black hole called Sagittarius A star. Like most large galaxies, the Milky Way has one of these giants at its core. And like many others, it pulls on stars and gas with an invisible grip that only gravity can explain. We know it's there because stars whip around something invisible and massive, something with the weight of over 4 million suns packed into a space smaller than our solar system. But unlike the black holes at the centers of some other galaxies, Sagittarius A star is strangely quiet. It doesn't rage with energy. It doesn't light up the surrounding space in bright X-rays or throw off powerful jets of matter. In fact, most of the time, it barely makes a sound. It flickers faintly. It dozes. For something that powerful, its silence is unexpected. Many galaxies have cores that shine brightly across the electromagnetic spectrum. Some are so bright, they outshine all the stars in the galaxy combined. These are called active galactic nuclei, or AGNs. They're thought to be powered by supermassive black holes, just like Sagittarius A star. The difference is that those black holes are feeding, gorging themselves on gas, dust, and sometimes even stars. As matter falls in, it heats up, spinning faster and faster until it glows with extreme energy. This process is what makes those galactic centers so bright. The Milky Way, however, does not behave that way. For reasons we still don't fully understand, Sagittarius A star is nearly dormant. It pulls in very little material. It doesn't produce powerful jets. It hardly shows up on X-ray scans unless it's having a rare moment of activity, a brief flicker of brightness that fades again just as quickly. One explanation might be that Sagittarius A star simply doesn't have enough fuel. In other galaxies, there may be more gas in the center, or more ways for that gas to get close to the black hole. Feeding a black hole isn't as simple as just having stuff nearby. Gas has to lose angular momentum. Basically, it has to slow down and fall in. If it keeps spinning around, it stays in orbit. It doesn't fall. In the Milky Way, there's gas in the central region, but it's not clear if that gas can easily get close enough to be eaten. Some of it might be held back by magnetic fields or turbulence. Some might be heated by nearby stars or supernova explosions. If the gas is too hot or moving too fast, it won't settle into the black hole. Another factor is that Sagittarius A star is actually not completely quiet. It's just very faint. In 2019, scientists using the Chandra X-ray Observatory reported flares of X-rays coming from it. These flares suggest that small bits of material do fall in now and then, causing a brief burst of activity. But the amount of matter falling in is tiny compared to what happens in active galaxies. There's evidence that Sagittarius A star hasn't always been this quiet. Studies of gas clouds near the center of the galaxy have shown signs that it may have been much brighter in the past. One clue comes from something called the Fermi bubbles, huge balloon-shaped structures that rise above and below the Milky Way's disk. These bubbles, discovered in 2010, are filled with high-energy particles and stretch tens of thousands of light-years into space. Their shape and energy suggest they were formed by a powerful event at the galactic center millions of years ago, perhaps when Sagittarius A star was more active. This history points to the idea that black holes can switch between active and quiet phases. They might go through cycles depending on what material is available and how it moves. Right now, Sagittarius A star is in a quiet phase, but it may not stay that way forever. Light echoes from molecular clouds near the center have revealed changes in brightness, like the shadows cast by a flickering flashlight. These echoes suggest that something near Sagittarius A star flared up a few hundred years ago. That flare would have been far brighter than anything we see now, though still dim compared to the most active galaxies. Despite these signs, the central question remains: why is it so calm compared to others? Part of the answer may come down to scale. Sagittarius A star is big, but not the biggest. Some galaxies have black holes with masses of tens of billions of suns. These enormous objects are more likely to find themselves at the center of large-scale flows of matter. Their galaxies may be more chaotic. They may collide with other galaxies, which dumps huge amounts of gas into the center, feeding the black hole and lighting it up. The Milky Way is relatively stable. It hasn't had a major galactic merger in a long time. It has small satellite galaxies orbiting it, like the Magellanic Clouds, but none that have recently crashed into it. That means less gas gets funneled into the center. The environment is calmer, so the black hole, left without much to feed on, stays quiet. Astronomers have also looked at the stars near the black hole. These stars form a tight cluster, moving at incredible speeds around Sagittarius A star. Their orbits have been tracked for decades, and from this data we've learned more about the mass and location of the black hole than ever before. But they don't seem to be falling in. If anything, they're keeping their distance. Scientists continue to observe, model, and simulate the behavior of gas and matter near the galactic center. They look at the effects of magnetic fields, star winds, and even dark matter. Each new discovery brings a little more clarity, but also raises new questions. The black hole at the heart of the Milky Way doesn't just pull in matter, it pulls in mystery. Perhaps one day it will flare up again. Maybe something will fall in, an unlucky gas cloud, or even a star, and trigger a new period of activity. Until then, Sagittarius A star remains an unusual example of a cosmic powerhouse at rest. Monster galaxies in the early universe. Too big, too soon. When astronomers point their telescopes toward the most distant parts of the sky, they are also looking deep into time. The farther away something is, the longer its light has taken to reach us. This lets scientists see what the universe looked like billions of years ago, just a few 100 million years after the Big Bang. But instead of small, chaotic, slowly forming galaxies, astronomers have been spotting massive, well-formed galaxies in the early universe, structures that seem too big and too evolved to have existed at that time. Some of them appear to be as heavy as the Milky Way, or even larger, yet they're seen at a time when the universe was just a few % of its current age. According to the standard model of cosmology, galaxies grow over time. They begin as small clumps of gas in the early universe, often forming stars at a modest pace. Through mergers and the steady pull of gravity, they grow larger and more structured. The process takes billions of years. So when scientists find galaxies that already look mature just a few 100 million years after the Big Bang, it raises tough questions about how such growth could happen so quickly. Some of the most surprising results have come from the James Webb Space Telescope, which was launched with the specific purpose of observing the earliest stages of the universe. With its powerful infrared vision, it can peer through cosmic dust and catch the faint glow of galaxies that existed when the universe was less than 1 billion years old. Almost as soon as it started sending back data, it began spotting massive galaxies where none were expected. In one early result, researchers found what seemed to be a population of galaxies dating back to around 500 to 700 million years after the Big Bang. These galaxies were large, bright, and packed with stars. Some estimates suggested they might contain up to 100 billion solar masses, a size difficult to explain given how little time had passed since the beginning of the universe. The surprise wasn't just their size, it was also how developed they appeared. Some had redder colors, indicating older stars. Others showed signs of ordered structure, like disks. If confirmed, this means these galaxies had already gone through phases of star formation, settled into shapes, and possibly even shut down their star-making activity, all before 1 billion years had passed. This isn't the first time astronomers have found early surprises, but the scale and consistency of the findings are unusual. Previously, Telescopes like Hubble had hinted at bright galaxies in the early universe, but their true mass and nature were hard to measure. With Webb's improved sensitivity and resolution, what had once been hints are now sharper, clearer challenges to accepted models. These findings raise the possibility that our understanding of how galaxies form and evolve might be incomplete. There are several potential explanations, but none are entirely satisfying. One idea is that early galaxies were more efficient at forming stars than expected. Perhaps conditions in the early universe allowed for quicker conversion of gas into stars. In this view, the early universe was a more fertile ground for building galaxies, and models need to be updated to reflect that. But even this explanation runs into limits, especially when the timeframes are extremely tight. Another possibility is that we're misunderstanding the measurements. Estimating the mass and age of a galaxy from its light is tricky. It depends on models of how stars emit light at different stages of their lives. If those models are off, especially under early universe conditions, then we might be misjudging how big or mature these galaxies really are. Still, many astronomers believe the basic results are robust. Even if the galaxies turn out to be somewhat smaller than initial estimates, they're still much bigger and brighter than expected. There's also a more dramatic possibility that something about the early universe is different than we thought. This could mean changes to the timeline of cosmic expansion or the behavior of dark matter. If structures formed faster than current models allow, that might hint at unknown physics at work in the early stages of the cosmos. One proposal is that dark matter, which plays a key role in pulling galaxies together, may have acted differently in the early universe. Or perhaps the initial distribution of matter and energy had more dense regions than expected, which led to faster formation. Across many observations, there now appears to be a general pattern. Massive, bright galaxies show up earlier than they should. It's not just a few outliers. It's a population of objects that could fundamentally reshape how scientists think about cosmic growth. Maybe there were bursts of rapid star formation that built galaxies in record time. Or maybe black holes and other exotic phenomena played a larger role in heating and shaping early galaxies than previously thought. The implications stretch beyond galaxy formation itself. If we revise how fast structures formed, we might need to rethink the timing of reionization, the period when the first stars and galaxies lit up the universe and changed its state. This process is central to our understanding of how light and matter interacted in the early cosmos. As scientists continue to gather data from Webb and other observatories, they're focusing on refining their measurements. Better spectra and more precise imaging will help confirm the mass, age, and structure of these early galaxies. At the same time, theorists are working to update their models to accommodate the surprising speed of growth. This may mean tweaking known physics, or in some cases, proposing new ingredients. The early universe remains one of the least understood periods in cosmic history. Each new observation brings more detail, but also more complexity. The monster galaxies that appear too big, too soon, are clues to a deeper truth about how the universe built its first great structures. Even as scientists debate the details, the broad lesson is clear. The early universe was more active, more crowded, and more productive than anyone had guessed. What was supposed to be a slow, steady process of galaxy building now looks more like a race, a cosmic rush to grow large and luminous under the strangest of conditions. Galaxies without dark matter? The Dragonfly, 44 conundrum. In 2016, astronomers using the Dragonfly telephoto array announced that they had discovered a strange galaxy called Dragonfly 44. It was located in the Coma cluster, about 330 million light-years away. At first glance, it looked like a faint, ghostly patch of light in the sky, almost invisible. But when scientists took a closer look, they realized this wasn't just a smudge of stars. It was a galaxy the size of the Milky Way, yet with far fewer stars. And more than that, it seemed to be made almost entirely of dark matter. Dragonfly 44 was labeled an ultra-diffuse galaxy. These kinds of galaxies are large in size, but extremely dim. They spread their stars out over a wide area, which makes them hard to detect. But even with their low brightness, they're still gravitationally bound. That means something is holding them together. And in the case of Dragonfly 44, it seemed that most of that something was dark matter, maybe up to 99.99% of its total mass. This would have made it one of the most dark matter-dominated galaxies ever found. The way scientists reached that conclusion was by measuring the speeds of stars inside the galaxy. In general, if stars are moving fast but not flying off into space, that suggests there's a lot of unseen mass holding them in. The faster they move, the more mass there must be. For Dragonfly 44, the stars were moving fast enough that it implied an enormous mass, far more than what could be explained by the visible stars alone. This discovery seemed to support the idea that dark matter is a crucial part of galaxies. Even galaxies that hardly have any stars still appear to be built on foundations of dark matter. But just a few years later, new observations would throw all of that into question. In 2018, astronomers working with another faint galaxy, this one known as NGC 1052 DF2, found something entirely unexpected. This galaxy, also ultra-diffuse, appeared to contain almost no dark matter at all. This finding went against the very idea that dark matter is a required ingredient in galaxy formation. If Dragonfly 44 was almost all dark matter, NGC 1052 DF2 seemed to have nearly none. It wasn't a one-time oddity either. Soon after, another galaxy, NGC 1052 DF4, was found with similar properties. Both galaxies puzzled researchers. They were roughly the same size and brightness as Dragonfly 44, yet they didn't show the same signs of hidden mass. The stars inside them moved more slowly, in a way that matched the visible material. There was no need to invoke dark matter to explain their behavior. This raises the possibility that maybe not all galaxies are built the same way. Maybe some galaxies form and evolve without dark matter, or lose it somehow. That's a big deal, because the entire framework of modern cosmology is based on the idea that dark matter is the invisible scaffolding of the universe. It pulls regular matter together, seeds galaxy formation, and shapes large-scale structure. Finding galaxies that seem to defy this principle could mean something important is missing from current models. Scientists began to look more closely at these odd galaxies. Could the measurements be wrong? Were there hidden factors that made the galaxies look like they lacked dark matter when they didn't? There were long debates about how distances were calculated, how star velocities were measured, and whether the galaxies were interacting with nearby objects that might have affected their dynamics. Some researchers proposed that maybe these galaxies had formed normally with dark matter, but then lost it due to gravitational interactions. For example, if a galaxy passed too close to a more massive neighbor, tidal forces could strip away its dark matter halo while leaving its stars mostly intact. In dense environments like galaxy clusters, these kinds of encounters are not uncommon. Others suggested that these galaxies might have formed differently from the start. Perhaps under rare conditions, it's possible to build a galaxy from gas alone, without the usual dark matter framework. But this would require a complete rethinking of galaxy formation theory. At the same time, questions were being raised about the original claims surrounding Dragonfly 44. Follow-up studies suggested that the early estimate of its dark matter content might have been too high. The number of globular clusters, small, dense groups of stars, used to infer the galaxy's mass was revised downward. Measurements of stellar motion were also updated, leading to lower mass estimates. Dragonfly 44, it seemed, might still have dark matter, but not quite the enormous amount first proposed. So now, instead of one clear story, there was a complicated picture. Some ultra-diffuse galaxies appeared to have a lot of dark matter. Others seemed to have very little. And scientists were left with a new kind of mystery: how galaxies so similar in shape and brightness could differ so much in their hidden mass. This put a spotlight on the role of dark matter in galaxy formation. It also drew attention to the tools and assumptions used to study it. Everything we know about dark matter comes from indirect measurements, like star velocities or gravitational lensing. When those measurements conflict, it forces scientists to ask hard questions about what they really know. Some physicists who have long been skeptical of dark matter proposed alternative explanations. One of these is modified Newtonian dynamics, or MOND. Instead of assuming there is invisible mass, MOND suggests that the laws of gravity behave differently at very low accelerations. According to this view, the motion of stars in galaxies doesn't require extra matter, just a new version of gravity. Galaxies that lack dark matter would pose a problem for MOND though, because under that model, the strange motion of stars is always expected. If a galaxy behaves according to Newtonian physics without hidden mass, that undermines the need for MOND as well. So in a way, these dark matter-free galaxies challenge both major views at once. They don't fit easily into the dark matter model, and they also resist alternative models of gravity. If such galaxies are rare, that tells us something about the specific conditions needed to make them. If they're more common than expected, it might suggest new categories of galaxy formation we've missed. And in either case, each discovery helps refine the models that try to explain the universe at large. The planet that wasn't, the fall of Vulcan. In the mid-1800s, astronomers believed they had found a riddle within our own solar system. Mercury, the innermost planet, had an orbit that didn't quite match predictions. It moved along an ellipse, as expected, but its closest point to the Sun, its perihelion, seemed to shift slightly over time. Most of that movement could be explained by the gravitational pull of other planets, especially Venus and Jupiter. But even after all known effects were accounted for, there was still a small leftover motion. This unexplained drift was tiny, just a few arc-seconds per century, but it refused to go away. In those days, Newton's laws were considered solid and unquestionable. They had explained the paths of the planets for nearly 2 centuries. Newton's gravity had even helped discover Neptune, based on irregularities in Uranus's orbit. So, when Mercury didn't behave as expected, the solution seemed obvious. Maybe there was another planet closer to the Sun, a small one whose gravity was nudging Mercury just enough to cause the strange precession of its orbit. That invisible planet was named Vulcan. The idea of Vulcan came to life in 1859 when a French mathematician, Urbain Le Verrier, proposed its existence. Le Verrier was no stranger to this kind of work. He had helped find Neptune using the same reasoning. He believed he could do it again. Vulcan, he thought, was orbiting the Sun somewhere inside Mercury's orbit. It was too close to the Sun to be seen easily, but perhaps it would show up during a solar eclipse or at dawn and dusk. Soon after Le Verrier's announcement, observers began to search for this hidden world. A few even claimed to see it. Reports of dark dots crossing the Sun's face were taken seriously. Some thought they had caught glimpses of Vulcan during eclipses or while the Sun was low on the horizon. But these sightings never lined up. The position of the supposed planet changed from one observation to the next. It didn't follow a consistent orbit. Most of the time, it couldn't be seen at all. Still, the theory hung on. For decades, astronomers kept searching. Telescopes were pointed near the Sun at every opportunity. Eclipse expeditions included teams specifically assigned to look for Vulcan. But the more time passed, the more uncertain the evidence became. No one could get a clear fix on this invisible planet. Its presence was always assumed, never proven. As astronomy advanced in the late 1800s and early 1900s, doubts started to grow. Other explanations were tested, but Newton's equations remained the standard, and Vulcan remained the placeholder. It was a neat solution to an uncomfortable problem. The thinking was that if you couldn't explain a motion using known bodies, maybe there was one more body out there that you hadn't found yet. Then, in 1915, everything changed. Albert Einstein had been developing a new way of looking at gravity, general relativity. It wasn't just a tweak to Newton's laws, it was a complete overhaul. Instead of treating gravity as a force between objects, Einstein described it as the warping of space and time by mass. Under this new framework, objects like Mercury didn't just follow curved paths because of forces. They moved along paths shaped by the geometry of spacetime itself. Einstein's theory was still new and untested, but one of its early results was that it naturally explained the precession of Mercury's orbit. The amount predicted by relativity matched the unexplained shift perfectly, 43 arc-seconds per century. There was no need for an extra planet, no Vulcan. The wobble wasn't caused by something tugging on Mercury. It came from the way space curved near the massive Sun. This was a major moment. For over 50 years, scientists had been chasing a planet that didn't exist. And now, in a single stroke, a new theory had removed the need for it. Vulcan was gone. The logic behind it had been replaced. That sort of reversal is rare in science. Usually, theories are refined, corrected, or extended. But in this case, a whole idea was discarded thanks to a deeper understanding of nature. Before relativity, the assumption was always that if something didn't fit, there had to be more matter to explain it. After relativity, it became clear that sometimes the rules themselves had to be questioned. In this new world, odd behaviors like Mercury's orbit weren't mistakes or clues to hidden planets. They were signs that physics was ready to evolve. Even so, Vulcan didn't disappear from memory overnight. It lingered in textbooks and stories for years. The name was recycled in science fiction, and later in pop culture. But in the field of astronomy, it became a cautionary tale. It reminded scientists that theories are only as strong as the framework they rest on. Vulcan existed because it had been needed by a theory that couldn't handle Mercury on its own. Today, astronomers are still careful when they run into unexplained motions or strange behaviors. The lesson from Vulcan is not to assume too quickly. Sometimes missing mass really is missing, like with dark matter. Other times, it's the model that needs to change. This was the case with Newton's laws and Mercury. And the only way to know the difference is through deeper investigation, better measurements, and openness to new ideas. The fall of Vulcan stands as one of the few times in astronomy when a planet was invented by math, accepted by scientists, searched for by telescopes, and then erased by a theory. And for many physicists and astronomers today, it's a story worth remembering. The upside-down orbits of hot Jupiters. When astronomers first began discovering planets outside our solar system in the 1990s, they were not sure what they would find. Most expected that these systems would look something like ours, small rocky planets close to the star, gas giants farther out. That's what the solar system had taught them. It made sense. The sun's heat would have burned off lighter elements near the center, leaving heavy, rocky materials to form the inner planets. Gas giants, like Jupiter and Saturn, needed colder conditions to form and hold on to their thick atmospheres. So they had to form farther out, beyond what's called the frost line. But those expectations were quickly overturned. The first confirmed planet around a Sun-like star was 51 Pegasi b, discovered in 1995. It was a gas giant, similar in mass to Jupiter. But it wasn't far from its star. It was extremely close. It orbited in just over 4 days. This meant it was incredibly hot, baked by the star's radiation. It was completely unexpected. A Jupiter-sized planet had no business being that close to a star, and this wasn't a one-time fluke. As more exoplanets were found, many turned out to be the same kind of object, large gaseous planets in extremely tight orbits. They became known as hot Jupiters. These planets presented a major puzzle. How could they form where they were? The temperatures in those regions would be too high for gases to condense. It would be like trying to build a snowman on a stove. In the early days of planet formation theory, this didn't fit. Something was clearly wrong. One idea that emerged was that hot Jupiters didn't form where they are now. Instead, they might have formed much farther out in the cooler parts of the disk, like Jupiter did in our own solar system. But then, after forming, they migrated inward. This process of planetary migration was something people had thought about before, but but it was considered rare or unlikely. Now, it had to become part of the standard model. These giant planets, perhaps through interactions with the gas disk they formed in or by gravitational nudges from other planets, spiraled inward toward their star until they were locked into tight, close orbits. But the story got stranger. As astronomers studied more hot Jupiters, they began to measure not just how far they orbited from their stars, but how they orbited. Using a technique called the Rossiter-McLaughlin effect, which looks at how the planet blocks light as it moves across the face of the star, scientists could figure out the angle between the planet's orbit and the star's rotation. In many cases, the planet's orbit lined up with the star's spin, just like in our solar system, but not always. Some hot Jupiters were orbiting at steep angles. A few were even orbiting backwards, moving in the opposite direction of the star's rotation. According to the classic model of planetary formation, all the planets in a system should orbit in the same direction. That's because they form from a spinning disk of gas and dust around the young star. The direction of that spin determines the orbits of the planets. The Sun spins counterclockwise, and so do all the planets. If you see a planet orbiting the other way, it means something dramatic must have happened. This led to a rethinking of what planetary systems can go through. One idea is that after a planet forms, it doesn't just migrate peacefully through the disk. It can be pushed, pulled, and even thrown around by the gravity of other planets or stars. If there's a nearby star in the system, a binary companion, it can tilt or disturb the whole disk. This might send a gas giant into a wild, looping orbit that eventually shrinks and flips. Another possibility is planet-planet scattering. Two large planets can get too close to each other, and one ends up being ejected or sent inward on a chaotic, tilted path. Over time, gravitational tides between the star and the planet can settle this orbit into a close-in position, even if it's retrograde. These processes are violent and messy. They are not the smooth, orderly system we imagined based on our own solar neighborhood, and they show that solar systems can evolve in ways we hadn't considered. The upside-down orbits of hot Jupiters were clues that the early history of many planetary systems might be shaped by instability, collisions, and reshaping events that leave behind strange survivors. It also raised new questions about habitability. If giant planets can move around like that, what happens to smaller Earth-sized planets that may be forming nearby? In many simulations, these giants clear out inner planets or send them flying into the star. If that's a common outcome, it might mean that systems with hot Jupiters are unlikely to also have Earth-like planets in safe, stable orbits. Or, if smaller planets survive, they might be on strange, eccentric paths of their own. Hot Jupiters became laboratories for studying planetary dynamics. They were easy to find because their size and close-in orbits made them excellent targets for the transit method and radial velocity measurements. And their strange properties gave scientists a chance to test ideas about disk physics, migration forces, and tidal interactions. As more data came in, patterns began to appear. Some stars were more likely to host misaligned planets, especially hotter stars. That hinted at deeper links between the star's properties and the fates of its planets. Even now, decades after the first discoveries, hot Jupiters are still a focus of research. Some are puffed up and swollen, probably from the intense heat they receive. Others show signs of atmospheric escape, with their gases being stripped away by the star. A few have comet-like tails of gas trailing behind them, and some are in such close orbits that they are literally spiraling in toward their stars, doomed to fall in over millions of years. These giant, close-in planets tore up the early models of solar system formation. They forced astronomers to rethink what's common, what's rare, and what's possible. Tabby's star and the megastructure hypothesis. In 2015, a strange signal from a distant star captured the attention of both astronomers and the public. The star, officially known as KIC 8462852, was located about 1,470 light-years away in the constellation Cygnus. It had been quietly observed by NASA's Kepler Space Telescope. which was designed to look for tiny dips in a star's brightness, signs that a planet might be passing in front of it. Most of the time, these dips are regular, predictable, and consistent. But something about this particular star wasn't following the pattern. The dips in brightness were irregular, dramatic, and completely unlike anything seen before. The star would dim by as much as 20%, sometimes for days, then return to normal. At other times, the dimming was smaller and faster. There was no consistent rhythm or period to the events, and the pattern didn't repeat in any clear way. This was unusual, and it didn't fit the behavior of a planet or even a set of planets. Planets block only a small fraction of light, typically less than 1%. Whatever was passing in front of this star had to be big, or there had to be a lot of it. And yet, the star itself didn't seem to be young or surrounded by the kind of thick dust cloud often seen in young systems where planets are still forming. The star's main discoverer, Tabitha Boyajian, led the team that first published findings on the strange light curve. Because of her work, the object became widely known as Tabby's star. The paper sparked a wave of curiosity. Scientists across disciplines began looking for natural explanations. Could it be a swarm of comets breaking up? A large disk of dust? A disrupted ring system? Some even wondered if the telescope had malfunctioned. But checks showed the data was solid. This wasn't a glitch. As the mystery grew, so did the speculation. One idea, raised almost as a footnote but quickly picked up by the media, was that this could be a sign of alien technology, specifically a Dyson swarm or some other kind of megastructure. A Dyson swarm is a theoretical collection of solar energy collectors that an advanced civilization might build around its star to harvest energy. These structures wouldn't be a single solid shell, but a loose group of panels or satellites that could block varying amounts of light as they orbited. The reason this idea gained attention was because no natural explanation at the time could fully explain what Kepler had seen. Even a cloud of comets, which had been proposed, seemed unlikely. A comet swarm that large and dense would be extremely rare, and it would also leave other traces, gas or dust, that weren't observed. Other stars with comets didn't behave like this. The alien megastructure idea, while far-fetched, had at least the advantage of matching the unusual dimming behavior, irregular, deep and complex. This kicked off a wave of follow-up studies and public interest. Crowdfunding campaigns raised money for ground-based observations. Telescopes around the world turned to Tabby's star, hoping to catch it in the act of dimming again. If it happened while the star was being watched in multiple wavelengths, from visible to infrared, it might give clues about what was blocking the light. If the object was dust, it would absorb more visible light than infrared. If it was a solid structure, the dimming would be similar across all wavelengths. Eventually, the star dimmed again. This time it was observed with better tools and greater awareness. The follow-up results pointed more toward dust than solid objects. The dimming was wavelength dependent, which suggested that small particles were likely to blame. This made the megastructure idea less likely. A fleet of alien solar panels would block all wavelengths equally. Still, the dust didn't fully solve the problem. The source of the dust wasn't clear. The star didn't seem young, and it didn't show signs of having a large debris disk. So where was this material coming from? One idea was that the dust could be left over from a disrupted planet or moon, torn apart by gravity, perhaps due to a close pass with another object. Another idea was that the dust was from a group of exocomets flung into tight orbits and slowly breaking up. There was also the suggestion that a large ringed planet or a group of planet-sized bodies surrounded by debris might be orbiting the star in a tilted, irregular path. All of these were efforts to fit the strange observations into known physics and behavior. Tabby's star remains one of the most unusual stars ever recorded by Kepler, and it raised a larger question about how astronomers deal with the unknown. When something doesn't fit, how far should scientists go in imagining possible answers? The idea of alien megastructures was never the main hypothesis among astronomers, but its early mention brought attention to the star and funding for its observation. It also opened the door to a broader conversation about techno-signatures, possible signs of advanced civilizations that might show up in strange ways, not just as radio signals, but in large-scale engineering. The case also revealed something about the limits of observation. Kepler could see the dips in light, but it couldn't tell what exactly was causing them. Ground-based telescopes added more detail, but not enough to close the case. Even space telescopes like Spitzer and Hubble offered only partial answers. Astronomy often works like this, observing clues from great distances, trying to reconstruct a picture from shadows and flickers of light. In that kind of environment, uncertainty is common, and sometimes speculation fills the gaps. Tabby's star shows that our models of star systems, while useful, are still based on a small number of examples, mainly our own solar system and the best-known stars. When something behaves differently, the first response is to question the data. The second is to look for a natural explanation. Only when both of those routes come up short does the third option, speculation beyond known science, start to surface. In the case of Tabby's star, that journey happened in real time, in public view, and with a level of media attention that few astronomical events attract. Today, the star is still under watch. New instruments, including those on the James Webb Space Telescope, may offer sharper answers in the future. If more stars with similar dimming patterns are found, it could point to a class of objects or processes that astronomers simply haven't categorized yet. If not, Tabby's star may remain a strange outlier, a puzzle without a full solution. But what it already gave was a powerful example of how science responds to the unexpected. The strange behavior led to a wave of observation, collaboration, and rethinking. The process included serious data analysis, careful modeling, and a bit of creative imagination. It showed that in science, mystery is not a failure, it's a starting point. Rogue planets, drifting in darkness without a sun. The idea of a planet without a star runs against what most people think of when imagining planetary systems. In our own solar system, every planet orbits the Sun. The planets move in predictable paths, held by gravity, warmed by light, and often shaped by interactions with each other. From Earth, we look out and see the planets as part of a family. Moons, asteroids, comets, all part of a system centered around a star. But the galaxy is far more diverse. Rogue planets show that some planets may have no home at all. One of the biggest challenges with rogue planets is that they are very hard to see. Planets don't produce their own light, and without a star nearby, they are not illuminated. This makes them nearly invisible in the traditional sense. Astronomers can't easily find them by looking for dips in starlight, as they do with exoplanets in orbit. They also don't show the kind of regular motion that could be tracked from Earth. Instead, the few rogue planets we've found have mostly been discovered by indirect means: gravitational lensing, heat signatures in infrared light, or occasional movement against the background of stars. Gravitational microlensing is one of the main tools used to detect these objects. If the lensing event is sharp and short, and if there's no sign of a nearby star to explain it, scientists suspect that the lensing was caused by a rogue planet. These detections are rare and unpredictable, but they've provided some of the best evidence so far. In 2021, a team of researchers announced the discovery of a candidate rogue planet using this method. The object, which appeared to be Earth-sized, had no visible star nearby. If confirmed, it would be the smallest rogue planet ever detected. Larger ones, similar in size to Jupiter, have also been suggested in past studies, including candidates in the star-forming region of the Orion Nebula. In some of these places, astronomers have spotted faint, moving objects that don't appear to be tied to any particular star. These detections are hard to confirm, but they hint at a wide range of possible rogue planets, from icy Earth-like bodies to massive gas giants. How do these planets end up without a star? There are two main ideas. The first is that rogue planets form in much the same way as regular planets, inside a disk of gas and dust surrounding a young star. But in some systems, especially ones with several large planets or chaotic early dynamics, one of the planets can be thrown out. A close encounter with another massive planet can give it enough energy to escape the system entirely. Once it breaks free from the star's gravity, it drifts into space. The second idea is more radical, that some rogue planets might form directly from collapsing clouds of gas, just like stars do, but without ever becoming massive enough to ignite nuclear fusion. These would be more like very small failed stars than traditional planets. Whichever the case, the existence of rogue planets forces scientists to rethink what a planetary system really is. If a planet doesn't orbit a star, is it still a planet in the same sense? Or is it part of a different category entirely? The definitions become blurred, especially with objects near the boundary between large planets and small brown dwarfs, star-like bodies that never fully ignite. For now, rogue planets are still called planets, but they live in a space outside the usual rules. They are part of the galaxy, but not part of any solar system. Some early studies have suggested that there could be as many rogue planets as there are stars in the galaxy, or even more. One estimate, based on microlensing data, suggested there could be up to 2 free-floating Jupiter-sized planets for every star. Other studies are more cautious, but even a smaller number would mean billions of these objects drifting unseen through space. They may be cold, dark and silent, but they are not rare. And while one might imagine them as frozen wastelands, that may not always be true. Some rogue planets could still retain internal heat from their formation, or from radioactive decay. If they are large enough, and if they have thick atmospheres or subsurface oceans, they could possibly harbor conditions suitable for life. This idea has been considered in various scientific papers. A thick hydrogen atmosphere, for example, could trap enough heat to keep a planet's surface warm, even without sunlight. And deep oceans, heated from below by geothermal energy, could exist under a crust of ice, similar to what's been proposed for some of Jupiter's moons. How do we ever learn more about such worlds? Without a nearby star to illuminate them, most rogue planets will remain hidden from view, detectable only when they happen to pass in front of a distant star, or give off a faint thermal glow. New telescopes may help. Instruments like the Roman Space Telescope, set to launch in the coming years, are expected to be especially good at microlensing observations. They could detect many more rogue planets and help build a clearer picture of how common they are. The Planet 9 hypothesis, mathematically predicted, still invisible. In 2016, 2 astronomers, Konstantin Batygin and Mike Brown at Caltech, presented a bold idea. They suggested that a 9th planet, roughly 10 times the mass of Earth, could be lurking far beyond Pluto, pulling on these distant objects with its gravity. It would take between 10,000 and 20,000 years to make a single orbit around the Sun. It was invisible, undetected by any telescope. But its gravitational influence, they argued, was clear in the math. This was not the first time a planet had been predicted before it was seen. In the 19th century, Neptune was found after astronomers noticed Uranus behaving oddly. Back then, irregularities in orbital paths led to predictions that turned out to be correct. Planet 9, if real, would be a similar case, an invisible presence revealed only by its fingerprints in the sky. The Kuiper Belt, a region filled with icy leftovers from the early solar system, extends from about 30 to 50 astronomical units from the Sun. The objects that sparked the Planet 9 hypothesis, though, were part of what astronomers call detached objects, or extreme trans-Neptunian objects. These include Sedna and 2012 VP 113, which follow orbits that stretch far out and never come close enough to the giant planets to be shaped by their gravity. Their orbits are not easily explained by any known forces within the solar system. And it's not just 1 or 2 of them. Several of these bodies appear to cluster together, with orbits tilted at similar angles, as if they're being herded by something large and unseen. Batygin and Brown ran simulations to test the idea. They found that a large, distant planet, perhaps 5 to 15 Earth masses, could naturally explain the observed clustering. It wouldn't just cause the objects to align in one direction, it would also cause some to flip into highly inclined orbits, even perpendicular to the plane of the solar system. And sure enough, some of these flipped orbits had already been observed. The pattern matched. But science demands more than explanation, it requires evidence. And here is where the problem lies. Planet 9 has not been seen. Despite years of sky surveys, careful searches, and increasingly sensitive instruments, no direct image has been captured. It could be that it's hiding in a region of the sky that hasn't been closely examined, or perhaps it's unusually dark, reflecting very little sunlight. Some think it may lie near the Milky Way's bright band, where background stars make faint objects harder to pick out. The lack of detection has led to a mix of responses in the scientific community. Some researchers support the idea, citing the strength of the orbital patterns and the success of simulations. Others urge caution. They point out that the apparent clustering might be the result of observational bias. Only a few telescopes are capable of finding objects that far out, and they tend to survey particular parts of the sky. If you only look in certain places, you're more likely to find objects that happen to be there. This could create the illusion of a pattern that doesn't truly exist. There are also alternative theories. Some scientists argue that the collective gravity of many small Kuiper Belt objects could be enough to shape the orbits of others. Instead of one large planet, the behavior might be due to the combined tug of thousands of smaller ones. Others suggest that past encounters with a passing star or an interstellar object might have disturbed the outer solar system, leaving behind a frozen pattern of orbits. Still, the Planet 9 hypothesis continues to guide research. It gives astronomers a reason to search, a specific set of predictions to test. If the planet exists, it would be one of the most significant discoveries in modern planetary science. It would reshape our understanding of the solar system's structure and formation. It would also raise new questions. How did such a large planet end up so far from the Sun? Did it form there, or was it pushed out by interactions with Jupiter and Saturn early in the solar system's history? Some even speculate that Planet 9 might not be a planet at all. A few researchers have suggested it could be a primordial black hole, a tiny, dense object left over from the earliest moments of the universe. This would be far more exotic and far more difficult to detect, but it's not entirely outside the realm of possibility. The gravitational effects would be similar, though the object would be far smaller and utterly dark. The hunt for Planet 9 continues with new tools. The Vera C. Rubin Observatory will scan the night sky with greater depth and regularity than any previous telescope. If Planet 9 exists, Rubin may finally spot it or rule it out. Until then, astronomers continue to monitor the motions of distant Kuiper Belt objects, looking for signs of unseen forces. The strange orbit of Neptune's companion. Most moons orbit in the same direction their planet spins. They tend to circle around the planet's equator, and their movements are usually smooth and predictable. These traits suggest they formed around their planets, growing out of the same cloud of gas and dust that once surrounded each young world. Triton is the largest moon of Neptune, and it moves in a direction that immediately stands out. It orbits the planet backwards, or in what scientists call a retrograde orbit. This means Triton circles Neptune in the opposite direction of the planet's rotation. It's an unusual trait. No large moon in the solar system behaves this way. Among the many satellites around gas giants like Jupiter and Saturn, retrograde orbits are found only among small, irregular moons, often captured asteroids or distant fragments. But Triton is massive. In fact, it's larger than Pluto. Its presence demands an explanation. This strange backward orbit suggests Triton was not born around Neptune. Instead, it was likely captured long ago. But capturing a large object in space is not easy. Space is not like a pool where friction slows things down. Out in the vacuum, a fast-moving object doesn't naturally settle into orbit. It just keeps going. For Neptune to capture something as big as Triton, there had to be a way for energy to be lost, for the object to slow down enough to fall into a stable orbit. Scientists have proposed several ideas to explain how this could have happened. One leading theory is that Triton was once part of a binary system. It may have been traveling through the outer solar system with a companion, a pair of icy bodies orbiting each other, like Pluto and Charon do today. If this binary pair passed close to Neptune, the planet's gravity could have disrupted their balance. In the right conditions, one member of the binary could have been flung away, while the other, Triton, was captured by Neptune. This kind of three-body interaction is rare, but possible. It would explain why Triton ended up in such a strange orbit, and why it is now a lonely moon without any known twin. After its capture, the moon would not have simply settled into a calm orbit. It would have approached Neptune in a chaotic path, likely looping in a wide and unstable route before gravity gradually pulled it into a tighter circle. During this process, Triton's orbit may have been highly elliptical, meaning it stretched far from the planet at times, then came close again. Such motion would have generated strong tidal forces, gravitational stretching between Neptune and its new satellite. These forces create friction, and over millions of years, that friction would have turned orbital energy into heat. This heating could explain why Triton, despite being in the cold reaches of the solar system, shows signs of geological activity. Its surface is young, smooth in many places, and marked by few craters. It has frozen plains and what appear to be icy volcanoes. When NASA's Voyager 2 flew past Triton in 1989, it saw geysers of nitrogen shooting from the surface, rising as high as 8 kilometers. This kind of cryovolcanism, volcano-like activity involving ice instead of lava, is extremely rare and suggests a dynamic interior. Triton's capture also left a mark on Neptune's moon system. The planet has fewer large moons than Saturn or Jupiter, and the ones that remain are small and irregular. Scientists believe that when Triton arrived, it caused chaos among the existing moons. Its massive gravitational pull may have disrupted their orbits, or even led to collisions. Some moons could have been thrown into Neptune or out of the system entirely. Triton's retrograde orbit, set at an angle to Neptune's equator, doesn't fit into a tidy framework. It's as though a stranger moved into a quiet neighborhood and rearranged everything. Neptune has other moons that behave strangely too, though none are as massive or as disruptive as Triton. Some of its smaller outer moons also have odd tilted orbits. These moons, with names like Nereid and Halimede, travel on stretched out paths and at high inclinations, suggesting that they too might be captured objects. Nereid, for example, has one of the most eccentric orbits of any known moon, sometimes coming in close to Neptune, then swinging far out again. It's possible that Nereid was once a regular moon, but got pushed into its current path by Triton's arrival. Other planets have moons that likely came from outside. Mars's two moons, Phobos and Deimos, are small and oddly shaped, resembling asteroids. Jupiter and Saturn both have groups of irregular moons, objects that orbit far out and at odd angles. But these tend to be small, and their orbits aren't as extreme as Triton's. What makes Triton so unusual is its size, its activity, and the clear evidence that it did not form where it is today. It may even have been a dwarf planet in the Kuiper belt, much like Pluto, before it was dragged into Neptune's gravitational grip. Studying Triton and the other irregular moons helps scientists piece together the history of the solar system. They offer clues about what the early solar system was like, how often giant planets encountered wandering objects, and how violent those encounters might have been. They also raise questions about planetary systems elsewhere. If Neptune could capture a dwarf planet, could similar captures happen around exoplanets? Could some of the strange companions found orbiting far-off worlds be the result of similar events? New missions may someday return to Neptune and take a closer look at Triton. NASA has proposed several ideas, including orbiters that would study the planet's atmosphere, rings and moons. These missions would carry modern instruments and provide far more detailed information than Voyager 2 could gather during its quick flyby. Scientists are especially interested in Triton because of its potential for subsurface oceans. If tidal heating kept its interior warm, there might still be liquid water beneath the ice, and where there's water, there's always a question about life. The wow signal, a message from the stars or a misunderstood Earth echo. It lasted just 72 seconds. A narrowband radio signal, picked up by a telescope in Ohio in the summer of 1977, stood out so sharply from the usual background noise, the man who saw the printout circled it and wrote one word in red pen: wow. That spontaneous note gave the signal its famous name, the wow signal. The Big Ear radio telescope, run by Ohio State University and dedicated to scanning the skies for signals as part of the search for extraterrestrial intelligence, SETI, was sweeping through a section of the sky near the constellation Sagittarius. Its job was simple: listen. Pick up faint radio transmissions and filter out anything that might be ordinary, like Earth-based signals, satellites, or cosmic noise. But on August 15, 1977, something very different came through. A spike of energy, strong and clear, appeared in a narrow frequency band around 1420 MHz. That frequency is significant. It's the natural emission frequency of neutral hydrogen, one of the most common elements in the universe. Because of its natural origins and the fact that it's rarely used for human transmissions, many scientists believed this band could be an ideal cosmic channel for civilizations to broadcast or listen. The signal didn't repeat. It didn't arrive in bursts or codes. It rose sharply, peaked, then fell away, like a beam sweeping past as the telescope moved. That shape matched what you'd expect from something stationary in the sky as the Earth rotated beneath it. In short, it looked exactly like what SETI researchers hoped to find: an artificial, possibly intelligent signal coming from deep space. Jerry Ehrman, the astronomer who spotted it days later while reviewing printed data, was stunned. The strength of the signal, measured in the printout as 6 EWJ5, was far above the usual baseline. In a code used by the project, the letters and numbers reflected the intensity of the signal, with higher characters representing stronger values. But that's where the mystery begins. After that brief window, the wow signal was never detected again. Not at that spot, not anywhere else. Follow-up observations, even using more advanced instruments, failed to find any repeating source. No patterns, no echoes, no confirming detections. It was a single event, never heard before and never heard since. In science, one-off events are always treated with caution. Without replication, it's hard to study the source or even be sure it was real. But the wow signal had too many unusual features to be easily dismissed. It matched expectations for an interstellar beacon. It came from a part of the sky not known for local interference. And it aligned with a protected frequency band that human transmitters generally avoid. If someone or something out there was trying to say hello, this might be exactly how they'd do it. Over the years, many theories have been proposed to explain the signal. Some point to natural cosmic sources, pulsars, quasars, or interstellar hydrogen clouds. But none of these have shown the ability to produce such a sharp, narrow, and short-lived radio spike at the specific hydrogen line. Others have speculated about Earth-based interference. Could a plane, satellite, or terrestrial transmitter have briefly caused the spike? This idea gained some ground in later years. In 2017, a researcher suggested that a pair of passing comets might have been responsible. These comets, 266 P/Christensen and 335 P/Gibbs, were moving through that part of the sky at the time and could have emitted natural radio waves. Hydrogen clouds around comets can, in theory, produce signals near the 1420 MHz frequency. But there was a problem. The signal was narrow and focused, while emissions from comets are usually weak and spread out. Moreover, the strength and clarity of the wow signal didn't match what's expected from cometary activity. Most scientists still find this explanation unconvincing. Other researchers have proposed a simpler explanation. Maybe it really was something human, but not recognized as such. Despite the Big Ear telescope being well shielded, radio interference is hard to completely rule out. Reflected signals can bounce off satellites, airplanes, or even space debris. Perhaps a stray transmission, military, commercial, or private, somehow mimicked a cosmic signal just long enough to be noticed. Skeptics pointed to the telescope's design. The Big Ear used a dual-horn setup to scan two regions of the sky about 3 minutes apart. A real cosmic signal would show up in one horn and then again in the second unless it ended or changed suddenly. The wow signal only appeared in one. This could suggest something local, an object or signal that passed briefly through the field of view. But again, the clean nature of the signal and its match to the hydrogen frequency keeps the door open to more exotic ideas. The possibility that the wow signal was a message, an artificial transmission from an intelligent civilization, still hangs in the air. SETI scientists have always said that such a discovery wouldn't come in the form of flying saucers or decoded alien languages, but in odd, hard-to-explain data. The wow signal fits that mold, and because it has never been definitively debunked or repeated, it occupies a strange space in scientific history. It's neither confirmed nor dismissed, it simply is. The mystery has inspired not just scientists, but also writers, filmmakers, and theorists. The idea that a single transmission from a distant civilization might be buried in decades-old data feels like something out of a novel. And yet, it's real. It's a line of numbers on paper. It's a blip in a telescope's memory. Despite the silence since, SETI programs have expanded. Modern efforts like Breakthrough Listen now use far more powerful telescopes and data systems. They scan billions of frequencies and analyze petabytes of data with the help of AI. And still, nothing has matched the clarity and singular impact of the wow signal. Even with today's tools, an event like the wow signal could still slip by, missed in the noise or lost to time. Some scientists continue to scan the same region of the sky, near the Chi Sagittarii star group, just in case it returns. Maybe it was a rotating beacon, sending signals in a narrow cone. Maybe we heard it because we were in just the right place at the right moment, and maybe one day the signal will sweep past again. Until then, the wow signal remains a symbol. It's a whisper in the dark, unanswered and unexplained, and it leaves us listening. The enigma of Oumuamua, asteroid, comet, or craft. When astronomers first spotted it in October 2017, they didn't know what to make of it. The object, moving fast and on a steep angle through the solar system, wasn't following the usual paths of asteroids or comets. It was something new, something uninvited and unknown. A Hawaiian word meaning a messenger from afar arriving first. It was the first confirmed interstellar object ever detected passing through our solar system. That alone was enough to make headlines. But it wasn't just where it came from that stirred debate. It was how it looked, how it moved, and how it didn't behave like anything we'd seen before. At first, scientists thought it might be an interstellar comet. Comets are known to come from the distant reaches of our own system, and if one had broken free from another star system, it might arrive looking similar. But Oumuamua didn't have the usual coma, the bright cloud of gas and dust that forms when comets warm up near the sun. There was no tail, no visible outgassing, nothing to suggest it was shedding material. It looked like a dry rock. Its shape made things even more confusing. Observations showed that it was tumbling as it flew, changing brightness in a pattern that suggested an elongated form. Some studies proposed it was at least 10 times longer than it was wide, maybe shaped like a cigar or a pancake. Either way, it was unlike any asteroid or comet previously observed. Most natural objects of that size are rounder, their shapes smoothed out over time by collisions and gravity. Then came the motion. After it passed closest to the Sun and began moving away, scientists noticed something odd. Oumuamua was accelerating slightly, just enough to be measurable, but not in a way that matched the influence of gravity alone. Something was pushing it. In comets, this is usually explained by jets of gas released as ices sublimate in the Sun's heat. But again, no such jets were seen, no visible particles, no light, no trace. That small but unexplained push was enough to open the door to more speculative ideas. In 2018, A paper by 2 Harvard scientists suggested that Oumuamua might not be natural at all. Perhaps it was a kind of light sail, an object designed to move by using sunlight as propulsion. They pointed out that if the object were very thin, even less than a millimeter thick, it could experience just enough pressure from solar radiation to account for the observed acceleration. That would require a design, not random formation, and that meant a possible artificial origin. The idea wasn't that Oumuamua was a spaceship, but that it might be debris or a probe, something left behind, discarded, or sent long ago by an intelligent civilization. It was, to be clear, a minority view in the scientific community. Most researchers favored natural explanations, but the fact that the artificial hypothesis was taken seriously at all showed how unusual this object really was. Many countered that the acceleration could still be explained by very fine gas emissions too small for our telescopes to detect, especially if the object had unusual material properties. Others proposed that Oumuamua might be made of exotic ice, like hydrogen or nitrogen ice, that could sublimate without leaving a visible trace. There were papers suggesting it might be a shard from the surface of a Pluto-like planet, or even a fragment shaped by the forces of interstellar space. Each theory tried to explain the same facts: the shape, the speed, the lack of visible tail, and the faint push away from the sun. But the data was limited. Oumuamua moved fast. It entered the solar system at about 26 kilometers per second relative to the sun, and by the time it was noticed, it was already on its way out. Astronomers had just a few weeks to observe it before it became too faint to track. Most of what we know came from telescopes looking at reflected sunlight. We never got a close-up. No spacecraft was nearby to intercept it. By the time its origin was realized, it was already gone. That brief window, combined with the object's strangeness, made it a perfect subject for controversy. It existed right at the edge of what could be explained and what had to be guessed. Some researchers saw it as a rare but natural visitor, a type of object we'd simply never seen before. Others saw it as a possible sign that we are not alone, or that our solar system is not as quiet as we once thought. Since then, scientists have begun to search for more interstellar objects, hoping to catch the next one earlier. In 2019, a second object, later named Borisov, was discovered. It was also from outside the solar system, but unlike Oumuamua, it behaved exactly like a comet, leaving a tail, shedding material, and showing a familiar pattern of movement. That made Oumuamua stand out even more. Borisov looked like a visitor. Oumuamua looked like an anomaly. There's also the possibility that we simply missed key information. Some researchers argue that with better equipment or earlier detection, we might have spotted signs that would have made the mystery easier to solve. Maybe Oumuamua wasn't unique, just the first one we saw. Others say it may be a type of object that forms in large numbers under special conditions, thrown into space by violent events in other star systems. Perhaps it was a fragment of something larger, shaped and stretched by tidal forces during its journey. But the artificial idea won't go away. It lingers because no single natural explanation ties everything together neatly. The shape, the acceleration, the lack of visible outgassing. It all adds up to a puzzle without a clear answer. Some researchers point out that extraordinary claims require extraordinary evidence, and we don't have that here. Yet at the same time, when the evidence is this unusual, even ordinary explanations can feel incomplete. Oumuamua's story is still being written. It may take years, even decades, before we fully understand what it was. Perhaps future missions will catch up with other objects like it. Some researchers have proposed using fast probes or next-generation telescopes to study interstellar visitors in more detail. Others suggest looking for more subtle signs, chemical signatures, unusual motions, or changes in light curves that might hint at artificial structures. Whatever it was, Oumuamua changed the conversation. It offered a rare moment when science and speculation touched hands, where serious researchers considered the possibility, however remote, that we might have seen a relic from someone else. In the end, we are left with a strange object that came and went without warning. But for a few short weeks in 2017, it made us look up and wonder if we had just glimpsed something we weren't supposed to see. The silence. Where is everyone? If the universe is as vast as we think it is, filled with billions of galaxies, each containing billions of stars, many of which are likely surrounded by planets, then why haven't we heard from anyone? Why hasn't any alien civilization sent us a signal, left us a message, or even just made themselves visible in some unmistakable way? This question, often called the Fermi paradox, is a riddle that sits at the core of astronomy, astrobiology, and even philosophy. The idea was first put forward in a casual way by physicist Enrico Fermi during a lunch conversation in the 1950s. He and his colleagues were discussing the possibility of intelligent life elsewhere in the universe. Fermi, after thinking for a while, reportedly said, "Where is everybody?" It was a short question, but one that captured a deep problem. If the galaxy is old and civilizations could arise with even a small chance, then by now, intelligent life should be everywhere. Some of those civilizations should be far more advanced than us. Some might have sent out probes, signals, or even traveled between stars. And yet there is silence. At first glance, it doesn't seem like it should be a problem. After all, space is big. Even the closest stars are light years away, and most of the galaxy is much farther. But the issue isn't just distance, it's time. Our galaxy is over 13 billion years old. Earth has been around for about 4.5 billion years. Humans, in our modern form, have only existed for a tiny slice of that time. So if intelligent life could evolve on other planets, and there are likely many with conditions similar to Earth, then it probably did so millions or even billions of years before us. That would have given those civilizations plenty of time to spread out, to make themselves known, or at least to leave signs behind. Even if faster-than-light travel isn't possible, slow expansion across the galaxy could still happen over millions of years. A civilization could send out robotic probes, settle nearby stars, and repeat the process. In just a few million years, a determined species could spread through much of the Milky Way. That's the core idea behind the paradox. There has been more than enough time for someone else to make contact or leave behind evidence. But when we listen for signals, scan the skies for signs, or look at other planets through our telescopes, we don't find anything. Not a whisper, not a trace. Just silence. This silence has led to dozens of possible explanations. Some are scientific, some are speculative, and some are unsettling. One possibility is that intelligent life is far rarer than we think. Maybe the conditions on Earth are extremely unusual. Perhaps the jump from simple life to complex, intelligent life is harder than expected. On our planet, life began relatively quickly, but it took billions of years for humans to evolve. That long delay might not be guaranteed on other worlds. Or maybe life is common, but intelligence is rare. Microbes could be everywhere, but thinking, tool-using species might be extremely rare. Another idea is that intelligent civilizations are common but short-lived. Maybe they destroy themselves before they can reach out to the stars. Nuclear war, climate collapse, or technological accidents could all end a species before it spreads. Some thinkers refer to this as the Great Filter, the idea that there's a step in the path to advanced civilization that's hard to pass. If the Great Filter is behind us and we've made it through, that would be good news. But if it's ahead of us, something no civilization can survive, then the silence of the galaxy could be a warning. Some speculate that advanced civilizations may deliberately stay quiet. They might fear attracting attention. If the universe includes hostile or dangerous species, then sending out signals could be like shouting in a dark forest. Better to stay hidden. This idea is sometimes called the dark forest hypothesis. In this view, everyone is listening, no one is speaking, and silence is a kind of survival strategy. Perhaps we simply don't know how to look or what to look for. Maybe alien communication doesn't use radio waves. Maybe it uses something we haven't discovered yet. Our current search is limited. We listen in narrow frequency bands for short periods, often with gaps in time. It's like trying to pick up a radio station by scanning just a few channels for a few minutes each year. We could easily miss something. Civilizations might send out signals in bursts or in formats we can't detect, or maybe they use technologies that are completely beyond our understanding, like quantum communication or gravitational waves. Some theories suggest we're not even seeing the universe clearly. The simulation hypothesis, for example, proposes that reality is an artificial creation, and what we perceive as space and stars could be limited by the rules of a system we don't control. In that case, other civilizations might exist, but we wouldn't be able to perceive them. There are also practical reasons why the search has come up empty. Space is vast, and our tools are still limited. The first radio telescope capable of detecting signals from other stars wasn't built until the mid-20th century. SETI has only been seriously active for a few decades. We've only looked at a small fraction of the sky for brief periods. It's like dipping a glass into the ocean and trying to conclude whether it contains fish based on that one scoop. Despite this, the Fermi paradox remains powerful because it's rooted in math and logic. If there are billions of stars, and even a small number of them have Earth-like planets, then life should have emerged many times. And over billions of years, at least a few of those life forms should have reached the point of intelligence and technology. Even with cautious assumptions, the numbers suggest we shouldn't be alone. Yet all we've found is a deep, still quiet. For some, the silence is comforting. It means we're unique, perhaps even special. For others, it's unsettling. It suggests that something might be wrong, that either the universe is much more dangerous than we think, or that we're missing something fundamental. The truth is, we don't yet know what the silence means. But it hangs over every signal we search for, every strange object we observe, and every unanswered question about life beyond Earth. Over the following decades, we may begin to close the gap between what the numbers say and what our instruments tell us. Or we may find that the silence continues, and if it does, the Fermi paradox will keep echoing in the background of every scientific effort to find our place in the universe. Dark energy, the anti-gravity force splitting the universe apart. In the late 1990s, two teams of astronomers set out to measure how fast the universe was slowing down. They expected to find a gradual deceleration in the expansion that began with the Big Bang. Gravity, after all, pulls things together. Over billions of years, they thought the gravity of all the matter in the universe, stars, galaxies, dark matter, would slow down the outward motion. But that's not what they found. Instead, they discovered that the universe wasn't slowing down at all. It was speeding up. The expansion was getting faster with time. Something was pushing galaxies apart, and not just gently. It was as if an invisible force had taken over the cosmos, pulling everything away from everything else. This was deeply unsettling. It meant there was a form of energy that filled space itself and worked in the opposite direction of gravity. They called it dark energy. The evidence came from Type Ia supernovae. These are exploding stars that always reach roughly the same brightness before fading away. Because they are so bright, they can be seen across huge distances. More importantly, their known brightness makes them useful as cosmic yardsticks. By comparing how bright a supernova appears from Earth to how bright it should be, astronomers can calculate its distance. And by measuring the red shift of the light, they can figure out how fast the universe was expanding when the light left that star. By doing this with supernovae at different distances, astronomers expected to build a map of how expansion had changed over time. What they found was the opposite of what gravity would do. Distant supernovae were dimmer than expected. That meant they were farther away than the models predicted. The universe had expanded more than anyone thought. The only way to explain this was if the rate of expansion had increased. Something was acting like anti-gravity. This discovery was one of the biggest surprises in the history of cosmology. It came from two groups working independently, the Supernova Cosmology Project and the High Z Supernova Search Team. Both groups announced their results in 1998, and both pointed to the same shocking conclusion. The universe was not just expanding, it was accelerating. In 2011, the leaders of the two teams shared the Nobel Prize in Physics for this work. But while the discovery was clear, the explanation was not. What exactly was causing this acceleration? The term dark energy was adopted as a placeholder. It refers to the unknown force or energy that is driving this expansion. Just like dark matter, it is dark because it cannot be seen or touched. It doesn't give off light or interact with other forms of matter in any known way. But it makes up most of the universe. Current estimates suggest that about 68% of the total energy content of the cosmos is in the form of dark energy. The simplest idea is that dark energy is the energy of empty space itself. This isn't a new idea. It goes back to Albert Einstein's cosmological constant, which Einstein dropped after Hubble discovered that the universe was expanding. But now, the cosmological constant is back. In today's models, it represents a fixed amount of energy in every bit of space. As space expands, more of it comes into existence, and so does more energy. This built-in energy acts like a pressure that pushes space outward. It's not energy from a source or particle. It's just there, part of the fabric of space itself. Why does this vacuum energy have the value it does? Theoretical calculations based on quantum physics suggest the amount should be far higher, by a factor of around 10 to the power of 120. This is sometimes called the worst prediction in the history of science. If those calculations were correct, the universe would have been torn apart long ago. Instead, the dark energy we observe is incredibly small, but not zero. No one knows why. Other ideas suggest that dark energy might not be constant at all. Maybe it changes over time. Maybe it's not a property of space, but comes from a new kind of field that fills the universe. These ideas fall under the category of quintessence, a term borrowed from ancient philosophy. Unlike the cosmological constant, quintessence would have dynamics. It could grow or fade or interact with matter in subtle ways. There are also more radical theories. Some suggest that what we see as dark energy might be a sign that our understanding of gravity breaks down at very large distances. These ideas are part of the effort to modify general relativity, just as some scientists have tried to change gravity to explain galaxy rotation without dark matter. In this view, the accelerating universe isn't a sign of something new pushing galaxies apart. Instead, it means that gravity itself behaves differently over cosmic scales. To figure out which idea is right, scientists are looking for more data. Projects like the Dark Energy Survey are designed to map the expansion of the universe more precisely than ever before. By studying galaxies, supernovae and gravitational lensing researchers hope to learn whether dark energy is truly constant or whether it has changed over time. Any sign of change would point to a new physics, something beyond Einstein's equations. The stakes are high. Dark energy determines the future of the universe. If the acceleration continues, galaxies will move farther and farther apart. Over billions of years, the night sky will grow emptier as more galaxies disappear beyond our view. Eventually, even nearby galaxy clusters could drift out of reach. The universe could become a cold, dark, and lonely place. In some theories, the expansion could speed up so much that it tears galaxies, stars, and even atoms apart, a scenario known as the Big Rip. In others, dark energy might fade, allowing gravity to slow things down again, or it could change direction, leading to a collapse, the opposite of the Big Bang, sometimes called the Big Crunch. Each outcome depends on the nature of this mysterious force we barely understand. Dark energy is a crack in the foundation of modern physics. It shows that our best theories are incomplete, and until we understand it, we can't claim to fully know how the cosmos works. Zero-point energy, the vacuum that refuses to be empty. In classical physics, a vacuum is simple. It's the absence of matter. Take everything out of a box, every molecule, every particle, and you're left with nothing. No air, no atoms, no sound, no light, just emptiness. That's the idea people had for a long time, especially before the 20th century. A vacuum was as close to nothing as you could get. But in quantum physics, this picture falls apart. The deeper we look into the nature of empty space, the more we realize that nothing is not truly empty. Instead, space itself has a kind of energy. This strange concept is known as zero-point energy. It comes from the idea that even in a perfect vacuum, when all matter has been removed and everything has cooled down to absolute zero, there is still energy left over. Space never truly rests. Zero-point energy is built into the structure of quantum mechanics. At the quantum level, particles don't behave like tiny billiard balls following fixed paths. Instead, they behave more like waves, always fluctuating, always uncertain. These fluctuations don't stop, even when systems reach their lowest possible energy state. In fact, quantum rules say they can't. There's a minimum amount of energy that must always remain. That's the zero-point energy, the lowest possible energy a system can have, even when it seems like there's nothing left to give. This idea can be traced back to the early 20th century, when physicists were developing the foundations of quantum theory. One of the first hints came from the study of the harmonic oscillator, a simple system used in physics to model many kinds of motion, from a swinging pendulum to the vibration of atoms. In classical physics, if you stop shaking the system, it settles to zero energy. But in quantum mechanics, even when it stops, a little bit of energy remains. This leftover energy exists because of the uncertainty principle, which says you can't know both the position and momentum of a particle exactly. That fuzziness guarantees a kind of background jitter, even in the calmest state. What's remarkable is that this energy isn't just a theoretical curiosity, it has real consequences. In the 1940s, Dutch physicist Hendrik Casimir came up with a thought experiment that turned into a real-world demonstration of zero-point energy. He imagined placing two metal plates very close to each other in a vacuum. According to quantum theory, the plates would alter the vacuum energy between them, restricting which quantum fluctuations could exist in the narrow space. Outside the plates, the vacuum could fluctuate freely. This imbalance, he predicted, would create a tiny force pushing the plates together, even though nothing seemed to be acting on them. Years later, scientists measured this Casimir effect in laboratory experiments. The plates did indeed move, proving that the vacuum wasn't empty after all. That was one of the first direct glimpses of zero-point energy in action. Since then, other examples have shown up, especially in the world of particle physics and quantum field theory. Every field, like the electromagnetic field or the Higgs field, has its own zero-point energy, and when you add all these up across all of space, you get a stunning result. According to calculations, the vacuum energy of the universe should be enormous, far higher than what we actually observe. This leads to one of the most puzzling problems in modern physics. If zero-point energy exists everywhere, and in huge amounts, why doesn't it overwhelm everything? Why isn't the universe torn apart by its own vacuum energy? The math says there should be enough energy in a single cubic centimeter of space to boil all the oceans of Earth. But we don't see anything like that happening. It's a gap between theory and observation so large that many physicists consider it a crisis. Some have tried to link zero-point energy to dark energy. Maybe the vacuum energy of space is what's pushing galaxies apart. That idea fits nicely in a broad sense. But there's a catch. The amount of dark energy we see in the universe is about 120 orders of magnitude smaller than what zero-point energy should be. This mismatch has forced scientists to rethink their approach. Some have suggested that our understanding of vacuum energy is incomplete. Maybe there's a cancelling mechanism, some process that subtracts most of the vacuum energy, leaving just a small bit behind. Others think we may need a new kind of physics altogether. String theory, loop quantum gravity, and other frameworks have tried to address the problem, but no solution has gained universal acceptance. Zero-point energy plays a role in atomic transitions, in quantum computing, and in the behavior of superconductors. It's even being studied in the context of virtual particles. short-lived particles that appear and disappear in a vacuum, borrowing energy from zero-point fluctuations. These virtual particles help explain many quantum processes, like how particles interact or how forces work at the smallest scales. Over the years, inventors and enthusiasts have suggested that zero-point energy might be tapped as a limitless energy source. If the vacuum contains energy everywhere, then in theory, we could extract it and use it to power machines, spacecraft, or entire civilizations. But the laws of physics aren't so generous. There's no clear way to extract energy from the vacuum without violating conservation laws or disrupting delicate balances, at least not with our current understanding. Still, the dream persists. Some have claimed to build devices that harness zero-point energy, but none have passed serious scientific tests. The energy is real, but it appears to be locked into the fabric of space itself, untouchable for now. It's everywhere, yet invisible. It shapes the behavior of particles, but can't be directly measured. It seems simple, but opens the door to some of the deepest questions in science. It blurs the line between something and nothing. In this sense, the quantum vacuum is not a void, but a stage on which the drama of the universe plays out. This idea has shifted how physicists think about reality itself. Space isn't just an empty backdrop. It has structure, it has energy, it can bend, expand, and ripple. It may even give rise to matter and force. Some theories suggest that the entire universe could have emerged from quantum fluctuations in a vacuum, a kind of cosmic birth from zero-point energy. As quantum mechanics continues to evolve and new technologies give us better tools to study the smallest scales, zero-point energy remains a frontier. It challenges our assumptions and reminds us that even the quietest, most empty part of the universe is humming with hidden potential. And with that, today's journey comes to an end. What topic would you like to see covered next? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.